Hello? So, it's already on. Excellent. Well, good morning, everybody. Welcome to the second FUNARCH workshop. It's going to be hopefully a relaxed and fun and educational day. If you were here for the past couple of days at ICFP, there was this relay race of 18-minute talks, so we have a little bit more time today. Let me introduce Perdita Stevens here in front, who's my co-chair, and we'll alternate running the sessions today. One of the pleasures of running a program committee is you get to choose somebody for a keynote speaker. And unfortunately, there's still sort of very few people who talk about functional software architecture. So there's been a lot of talk at ICFP on mechanizing various aspects of semantics and doing compilation or deriving compilers and stuff like that, but how to actually do functional programming. Very few people, are on record talking about that specifically in recent years. So I was very pleased to find somebody who's local to Milan to come here. So Marco Sampellegrini is going to talk about some of the things dear to my heart as well, specifically about things like domain-driven design. So looking forward to your talk. Go take it away.
Okay, does this work? Yeah, hello everyone. Thanks for being here. As Michael said, I'm going to be talking about functional software architecture. A little bit about me. I'm Marco. I work for a company here in Milan called Salupei. We build products for the private healthcare sector. And our offices are not too far from here, actually. And a couple of projects that I've released over the past few years that could be of interest to you are the Simple Haskell Handbook, which is a very hands-on book where you get to build a continuous integration server in Haskell from scratch. And a more recent project is a compiler for a new programming language called Borgo, which is a sort of Rust-looking language that compiles to Go. And obviously, I've no background in compilers or anything like that, so it's the result of me trying to learn and build something that almost works. Before we get to talk about software architecture, I think it's helpful to look at how we build software in the small. So maybe we have a new project and there's only a few people working on it, and we have a small code base, and this is where the tools we know and love in the functional programming world are really helpful, and you can get the most out of them. So in a small project with a single code base, you can really take advantage of static typing. You can even go as far as using fancy types. There's a lot that you can encode at the type level. And all of this is possible because there's a single compilation unit, and at the end of the day, you're only releasing a single binary. So statically checking the entire software is possible at this stage. And one of the things that has become popular over the past few years is this mantra of trying to make illegal states unrepresentable. And this is actually doable in small projects or projects that end up being compiled as a single unit, because you have control over pretty much the entire thing. The problem, I think, with this approach is that it doesn't scale too much when the project grows, and so there are multiple teams involved, and possibly the code base gets split up into multiple different code bases. There are multiple services that get deployed, and so when a project becomes this large, it's actually harder to statically check the entire thing in one pass. And a lot of the times it's impractical to do so. And even if you're using the same tech stack across all services and across all teams, you might still end up having, different compiler versions or different library versions, and it's really hard to statically know that what you're running in production is actually what you're expecting. And yeah, in a large system, it's best to assume that impossible states will actually happen, and so that, I think, is where software architecture start to become important, because there are, methodologies and practices that can help when our tools, are less helpful. So a little bit of a disclaimer: this talk is not going to be about microservices, or it's not going to be arguing about monorepos or multiple repos. It's definitely not going to be about Haskell or any specific language. It's not going to be about service meshes or any specific technology about any orchestration tool. I think software architecture is one level higher than these concepts, and so we're going to be looking at that. So software architecture really, in my opinion, is less about the technology itself, and it's more of a communication, it's more about solving communication issues, both at a technical level, certainly. So you have to find a good way for all of these services to communicate and exchange data with one another. But most importantly, it's about solving the communication problems that arise among teams and even within teams itself. Yeah. So software architecture is about finding techniques that work to solve these communication issues. And one of the methodologies that has come out over the past few years is domain-driven design. The book that popularized DDD came out in 2003, so it's more than 20 years old now. A lot of the stuff I'm going to be talking about is not particularly novel, but it has worked well for a lot of companies, and it's perhaps topics that we don't talk about that much in functional programming circles, but they're extremely popular in mainstream, programming circles, and I think there's a lot we can learn from that. And so domain-driven design is sort of an umbrella term. There's a lot of techniques and methodologies that are under the domain-driven design term, and I cannot possibly cover all of them today. So I'm going to just be talking about a few of them that I think are interesting and particularly relevant to functional programming. So in particular, to solve the communication issues between humans, I think the ideas of using an ubiquitous language and defining a bounded context are particularly helpful. So defining an ubiquitous language means that within a team there should be a shared vocabulary and a shared terminology that everyone in the team uses when discussing the software and features and bugs. And this is not just the engineering team, but also the business people, the stakeholders, the domain experts. They should all agree on a specific vocabulary that they use when discussing the software. And the other important aspect is that in a large project, you probably have multiple teams, and each team has ownership and is responsible for a particular perimeter. And so this perimeter is defined as the bounded context in DDD. And within this bounded context, there should be a specific vocabulary, a specific ubiquitous language that is used within that team. And so a certain term might have a specific meaning for one team, but it could have a completely different meaning for another team. And I'm going to show you an example of this to make it clearer. So as I said, I work for a healthcare startup. So this is an example, a real-world example that I came across over the past few months. And we specifically have two bounded contexts. One is what we call the payments bounded context, and the other one is the insurance claims. And so we build products for clinics and hospitals, and for the payment product, you have the customer coming to the clinic, they want to receive some treatment, and they have to pay for this treatment. And in that case, we only need to collect a few information about the customer, because we only need to process the payment, and so we don't need that much data. And so the term customer in that bounded context has a very specific meaning. In the insurance claims bounded context, on the other hand, we no longer refer to the customer as a customer, but we adopted the patient term because we thought it was more fitting. And in that case, we actually need to process a lot more data about the person that comes in and wants to pay with their insurance policy, because we have to collect, a lot more data about their date of birth, their address, their social security number, their medical history. And so even if they seem, the same entity from outside, we're still talking about customers. They're actually different, and it really helps when discussing, features and stuff with the rest of the team to use the proper terminology. The same goes for invoices. In the payments bounded context, we are the one emitting the invoice, whereas for the insurance claims, we are only processing invoices. So same terminology, but very different use cases. My favorite thing about domain-driven design is the idea of event sourcing. And so the idea that events are actually core to your software system and should be core to your software architecture. And the idea with event sourcing is that you have a durable append-only log of events, and anytime there is a state change in the system, instead of imperatively going to the database and updating some row, for example, you would instead emit an event that you append to your event log. And the result of this is that all application state is derived from events that are persisted in the event log. The great thing about events is that they're strongly typed. They have a very specific schema, and they're versioned. So in the beginning, I said that when a project grows, you tend to lose a little bit of the benefits of using static typing, and you tend to lose a bit of type safety because of all the services involved. But I think event sourcing actually allows you, it allows you to gain back some of these benefits, because you know that all of the events in the event log have a specific schema. And so in this case, if we take an e-commerce platform as an example, we might have an order created event which tracks all of the data related to a specific order, like the customer that made the purchase, the items in the order, the amount, and stuff like that. Once we have all of these events, we can then have consumers that go through the event log and process them. And so we could have a consumer, for example, that populates an order table in an actual database. And so we go through all the events in the event log, and whenever we see an order created event or an order updated, order deleted event, we run the corresponding query on the database table. And this allows us to effectively have the same read model, the same view over our data that we had before, but it actually enables us to go through the event log another time, and maybe 6 months down the line, we realize that we actually have some access patterns where cache, like a Redis store, would be helpful to access data from the orders in a more performant way. And so we can have another consumer that goes through the event log once again and populates a Redis cache with the correct data. And the most important benefit of using event sourcing is that it allows you to achieve decoupling and team independence. So decoupling between all of your services. You no longer have the order service that is responsible for exposing all of the data for an order, for example. But if, let's say, the billing service needs to read information about orders, instead of going to the order service and ask for specific information, they can just consume the log independently, build their own consumers, and pluck out the events and the data that they need. And this to me is the most important aspect of event sourcing, and the thing that tends to build a good software architecture in a large system. The alternative to this in large system is traditionally using RPC. So you have all of your services, and when they need to know something, they just send a request to another service, and that service replies with some data. But this approach encourages tight coupling between all of your services, and there's actually a lot of drawbacks to architecting your system in this manner. One drawback, as I said before, is that now the order service, for example, is responsible for exposing data that the billing service needs, but that the order team and the order service doesn't find that useful. It's not actually data that they care about. And so it introduces a lot of tension between teams, because now the billing team is blocked until the order team gets around to exposing that data. But there's also, problems that arise with access pattern and unforeseen issues when some service starts to, send a ton of requests to another service, and they were not ready for that, for receiving that amount of requests. And so the order service, as a result, goes down, and all of the dependent services go down as well. And this can bring down the entirety of the system, and it's not a fun place to be in. When you use RPC, you typically use some sort of a serialization protocol. Typically, that is protobuf and gRPC. And so protobuf is great because it's very efficient. It's a binary protocol, and you can cram a lot of data in a very small packets. But the problem with protobuf and similar protocols is that they're not very type safe. So we said that one of the benefits of using events is that you have a fixed schema, and events have a specific type. But protobuf in particular doesn't even have the notion of a required field, and so the documentation encourages you to use comments to indicate which fields are required in your schema. But this is not really, a solution that has that should be acceptable, in my opinion. So another benefit of event sourcing is that you have an audit log for basically free, and if you need to find out what happened at a specific day and time, you can just go through the event log and, either for debugging purposes, you can track everything that has happened, or for security and compliance purposes, you can look at everything that, is relevant to a specific order or a customer or something like that. However, event sourcing also comes with some drawbacks. One is related to privacy and GDPR in particular here in Europe. When a customer wants all of their data to be erased, it's very easy to erase that data from a database table, for example, but it's less practical to erase events from an event log because it's meant to be append only and immutable. So one technique I found to be really helpful here is to actually encrypt all of the personal information in an event. Instead of having them in plain text, you encrypt them with a unique key specific to that customer, and you store that key somewhere else, so that when you need to erase all of the data for that customer, instead of having to go through the event log and delete all of the events, you can just forget the key and you can no longer decrypt those events. And the other big issue with event sourcing is that if you're handling large amounts of data, like millions of events generated in a short time frame, you need to find a data store that is able to handle that kind of load. And Kafka is particularly handy in this situation, but there are also techniques that you can use to reduce the amount of data in the event log itself. So snapshotting is one such technique where you take a batch of events and you sort of compress them in a single event, so that there's not as much data in the event log and it's a bit more manageable. So in closing, I think software architecture, in my opinion, it's really about solving communication at two different levels. One is solving communication between humans, and that's where domain-driven design has a lot of methodologies and techniques that can help with that. One we haven't touched on is event storming, which is another technique that I found really helpful. And the other issue that software architecture should be concerned with is obviously solving communication between services. And that's where event sourcing is particularly helpful, in my opinion. And a book recommendation, which is not specific to software architecture, but there are definitely topics in this book that are related to software architecture. The book is called Designing Data-Intensive Applications. It came out a few years back. One of the quotes from the book that I really like is that the fastest and most reliable network request is the one that you don't make. And event sourcing allows you to do precisely that. So the system is more reliable and even more understandable, in my opinion, as a result of not having a ton of network requests being made from service to service. And going back to the thing we were saying in the beginning about making illegal states unrepresentable, in my experience, it really pays off to be paranoid, as suggested in this book. So if you think the system cannot get in a specific state, you would actually be better off, programming and programming against that situation as well, because eventually, what you thought was impossible will eventually happen. And in a large distributed system, this is even more relevant. Yeah, so this is all I had to say. Thank you for attending. Yeah.
Paranoid, and how do you balance that with the prioritization of making the software?
Yeah, so the question is, how do you balance paranoia with prioritizing anything else like feature development, I guess. I don't think you should balance it with like with velocity itself. It's more a balance with how much type safety you want to encode or you want to have in the system. So handling errors should be something that you do regardless of how paranoid you are. It's more about how how many invariants you want to encode at the type level, and how much you want your types to be to follow the happy path, if you will. So in my mind, it's more about putting less constraints on at the type level and be a little bit more lenient in that sense, and maybe use a little bit less fancy types and stuff like that, so that when something unforeseen happens, you're actually able to handle it. It's less about prioritization and velocity. I don't know if that answers the question.
Yeah, thank you.
Hi, my name is Edwin. It's a very interesting talk. I have a question on error handling. So let's say you had a bug in the code that creates your event source, and there is something there, and you want to correct it. But now you've already taken some decisions based on the bad data. So how do you deal with updating some historic value that you now know is wrong? And maybe you fixed it, but how do you deal with updating everything that came from it?
Yeah, very good question. So the question is how, if you put the wrong data in an event, given that the event log is immutable, how do you then fix that bad data? So ideally, you would bump the version of the event with the bad data. And so now you have the same event at two different versions. And in a new version, you populate the event with the correct data. That's assuming the schema is the same in both versions. And slowly you start to migrate consumers from the previous version to the new versions. And this is not always feasible depending on how many consumers you have, but that I think is the ideal approach. If you can't do that, you probably would be, like, another alternative is to just make another event that specifically fixes the previous event that contains bad data. I guess the trade-off here is for how long did this happen and how much data did you already store. If it's a short time frame, I think it's worth upgrading the event and try to populate the event log with the correct data so you can forget the previous version. But if it occurred for a lot of time and there are other services that like the bad data has spread in the system in a sort of uncontrollable fashion, it's best to keep that the previous version in and try to fix it with new events that correct the bad data.
Hi, James Chapman, Input Output. I was wondering, you mentioned having a common vocabulary, and I was wondering if you see that as like kind of expanding the vocabulary or more kind of settling on common terms to reduce ambiguity. Okay,
so this is an interesting topic because I think if you can, you should use as few terms as you can, but the important aspect here, I think, is that each team should have their own vocabulary. So if you take the entirety of all the terms used within the company, you might have thousands of terms, perhaps. But the thing that DDD advises for is that within a single team, you should have only you should use only the terminology that matters for the team. And perhaps the strange thing is that the same term could be used in many different bounded contexts across different teams, and the semantic of the same term could vary quite a bit between teams. And so each team should have, in my opinion, the smallest vocabulary they can get away with. And they shouldn't be too worried if a term has a different meaning and connotation in that team compared to another one. And the fact that a vocabulary can grow and expand, it's not ideal, but depending on the complexity of the domain, it might be unavoidable.
Thank you.
I guess as kind of a follow-up to that, how do you balance the tension between when teams need to communicate with potentially conflicting definitions of the same term, like the example you gave of invoice between customer and sales?
Yeah, good question. I think the thing that allows different teams to communicate, I think, should be the domain event first and foremost. So each event should be owned by a specific team, and they should define the semantics of that event. And so when an event is not internal to a specific team, but is sort of a public event because it can be consumed by other teams, there's definitely some terminology and vocabulary that spills over a bounded context, and you should be really careful in defining what an invoice in this case means for that specific event, because it's very important.
What do you think, or what has your experience been with the impact these techniques have on end users? So for example, by going to an architecture like this, you become eventually consistent, right?
Right.
And so users might run into certain kinds of bugs where they just don't understand what's going on. And I'm just curious what your experience has been with that.
Yeah, good question. I think this is actually one of the most discussed topics in the book I was talking about before. So I think that the problems with eventual consistency are, natural in a large distributed system. They're definitely more apparent when using event sourcing, but the problem of reading your own rights essentially is it's a problem regardless in a large system. Because maybe you have a large database cluster and you're writing to the primary, but then you refresh the page and you're reading off a replica, and that replica might not have the most up-to-date data yet. And this is a problem regardless you're using event sourcing or not. But with event sourcing, it's even more apparent, because you write an event to the event log, but now you have to wait for the consumer to consume that event and see that event and actually write to the database. And this, I think, there's another technique called CQRS, which can help with this. And essentially with CQRS, typically CQRS and event sourcing are discussed hand in hand, even though they're not, you don't have to use them together. The idea behind CQRS is that you have a write path and a read path. So you send commands to your API or whatever, and you enforce some business logic, and then you write an event as a result. And then you have a read path that only reads data from the projections that the consumers created by reading those events. And so here the trick is to have some sort of a UUID attached to each command. And so if I'm sending a command, for example, to create an order, in the request I send to the right path to create that order, I also attach a UUID. And then I can ask my read layer to only respond if you have already processed the event with that UUID. And so it's not perfect, but because there's typically some polling involved, either at the at the read layer or on the client side, waiting for that specific UUID or command to be available. But that's that's the technique I've used in the past to make sure that you really are consistent with the data you read. And in a lot of cases, it's not necessary to achieve this level of consistency, but obviously if you're reading, if you just created an order, you expect it to be there in order to show it to the customer.
You mentioned that a good feature of this is that everyone has access to it, so you don't need to pass requests around. But especially in the health situation, I was thinking like, oh, everyone has access to my health data. Amazing. That's what I want. You kind of alluded to it with the GDPR, but that doesn't really strike me as solving who should and shouldn't have access to it. So
fair enough. Yeah.
How do you do that?
So by everyone, obviously, I mean every service or team within the company, but it's still a valid concern. So if you have a single event log, all of the events go through it, and unless you use some other encryption methods, each team will have access to all events. I think if you wanna, at some point you have to trust, I guess, your teams, and I don't think it's particularly helpful to be overly paranoid about who has access to the event log. It's more of an infrastructure problem here. You want to make sure nobody from outside can access your systems. But one way to solve this would be to split your event log further. And so healthcare data maybe is only stored in a particular log or partition or whatever, so that only certain services can access it and read it, whereas all of the other events are stored elsewhere. But I think, I would rather make sure that we are good on the infrastructure side and we run penetration tests and auditing so that no external actor can access our systems, rather than not trusting the teams within the company. But it's a valid concern, and I would probably split the log further so that you have further, authorization between teams.
But so just to follow up on that, would it be then a fair characterization that event sourcing is a good approach if permissions is not inherently a problem? But once you have permissions, then you have all the other problems of having to pass around requests, or you mentioned having multiple queues, but now you need to have something that communicates between queues. So fundamentally, you're back to the old thing. So would that be fair? And therefore you would say like, this is a solution when, for instance, permissioning is not an issue. But when that's an issue, then who knows? Maybe the trade-offs are different.
Yeah, to expand on that, so the alternative in an RPC style architecture would be that health service owns all of the very sensible data, healthcare data, and so in order for another service to read that data, they would have to send a request, and they would have to be authorized in some way by that service. And this way you can ensure that that the healthcare service owns that data, and it doesn't, no other service can access it. I guess that's the alternative. So it's, I think what you said is spot on. If you need that granularity of permission, then probably storing everything in the event log is not a good way, unless you encrypt the data before it's written inside the event log, and if only a certain service needs to have access to it, then probably, in all likelihood, they are the only one owning the key to decrypt that data. Maybe that's another way of looking at it.
So,
That's all very interesting. Thank you very much. I wonder if I can get you to say a bit more about what's functional about this, because I'm sitting here thinking in terms of somebody perhaps programming in a typed imperative language, and I'm not hearing anything that wouldn't apply.
Right, yeah, so I think event sourcing should sound really familiar to functional programming crowd, because it's essentially, a state machine. It's what we do when architecting functional software, in my experience. So you have some state with some type, and then you have an ADT, an event ADT with all of your events as a discriminated union. And whenever an event comes in, you take the existing state and then you output the new state. And so this is sort of the simple idea of having a state machine, glorified and applied to a larger architecture. And obviously, if you can operate in memory and do it all in a pure manner, like you're often able to do in a small setting, in a small code base, then great. You get to benefit from all of the tools and static typing and fancy types that we talked about in the beginning. But in a larger system, you can still have a functional approach to this. But as you said, you can use this with whichever technology, and it doesn't always apply. It doesn't only apply to Haskell, but I think the mindset, the functional mindset, is still relevant even in a larger context. Yeah.
So first of all, I really like that you made the book known as the Blue Book in the DDD circles pink. Yeah. So if you talk to DDD people and they mention the Blue Book, it's the book that was pink here.
That's the Blue Book.
Yeah, that one. That's the Blue Book, obviously. So, I mean, DDD is great, right? Functional programming is great, but you talk mostly about something called strategic domain-driven design, right? Which is about splitting your system so you can work on it with several teams, right? And then, you go down this path with event sourcing. And now, but the thing that happens now is you have all the upsides of strategic domain-driven design, but you have the downside of the fear and paranoia of distributed systems, right? So it's a trade-off. Yeah. Is that a necessary trade-off, you think?
Could you be a bit more specific with your question?
Well, do I really have to, if I do all of strategic design, right? I then identify my subdomains, I identify my bounded context, I assign different teams to the different bounded contexts. Yep. Do they really have to develop a distributed system? Is that
I see.
Right?
Yeah, no. DDD that can definitely be applied regardless of the size of the system, I guess. And it doesn't, the result doesn't have to be a large distributed system at all. I'm actually, a big fan of monoliths, and I think you can push a monolith quite far. So yeah, this is my experience with the systems I worked with, and a lot of the times I didn't agree with, all the splitting and the architecture nonsense sometimes that came as a result of following the microservices trends. But you can definitely, apply all of these strategic domain-driven design to any software system, and you can definitely, still have multiple systems, each responsible for a part of a monolith without having to split things up in multiple services.
So if I can make a comment on that,
yeah.
So I agree with you that there should be, or there are ways of developing even one monolith with multiple teams, right?
Yeah.
But I think the basic assumption of the domain-driven design community is that they don't know how to do this, right?
Okay.
Also, I mean, there's certainly efforts to sort of develop monoliths. I mean, the DDD community certainly recognizes the problems with introducing distributed systems, right? I mean, domain-driven design is used to develop some very large and high-volume systems, but not all of them are like that, right? And so you don't need distribution to achieve performance. But I think the underlying assumption until fairly recently in the domain-driven design community was that the monolith is always unmodular, right?
Right.
So, which is why they've now introduced this there's this new term going around now, it's called the modulith.
Yeah, true.
Sort of, making very clear that, well, you say monolith, you mean something unmodular, and like the modulith is like takes this extra effort, right? To you've got to go. I mean, there's all kinds of technological things that people are trying out right now in order to achieve. Now, I think to the functional community, this seems kind of. Do you think the functional community or the technologies that you work with can contribute something to achieving the modular monolith that maybe is not so prevalent in the domain-driven design object-oriented community?
Yeah, I think there's something to be said there about people eventually making a mess of any single code base. So a monolith in principle is great, but if you're building it in Java, for example, or without any without a fundamental philosophy or technique, and you're just abusing all of the OOP madness that you can do, then you tend to blame, the monolith itself for the mess that has resulted, instead of the poor techniques that have contributed to it. So I think in the functional programming community, we have a much more principled approach to this. And so a monolith is definitely much more attainable on our side, I think, because we are perhaps much more diligent when building our programs, and the fact that you have constraints enforced by the language, and you have to, the language, and I'm talking about Haskell here, but that if the language forces you to work in a pure setting, for example, and have a pure domain core and an imperative shell, then it's way harder to make a mess, I think, and this can scale to quite a large code base without needing to split things up. Like in the end, I think the necessity to split things up is more due to getting away from a code base that has gone out of control, and it's messy and nobody wants to work on it, rather than it doesn't scale, or there's some fundamental problem to a monolith that cannot be solved.
So if I can ask one more question. So again, you talked about strategic domain-driven design, but there's also tactical domain-driven design.
Mm-hmm.
So there's, of course, the ubiquitous language, but did you find anything worthwhile for functional programmers in tactical domain-driven design? I don't think I want a super long answer, but...
Yeah, I don't know if it... like the other things that I find helpful in DDD, and I don't know if they are under the tactical DDD side, but I think they are, it's the concept of entities and aggregates. And so the idea behind an aggregate is very simple. It's basically anytime there's a business logic decision, or you have to enforce some invariant for a specific model or a cluster of models, again, you have your state machine effectively that takes the existing state of the model, the command or the thing that wants to update its state, and you can run, you can encapsulate all of the business logic and invariants under this aggregate, which basically enforces that it's always in a good state. And the concept of using entities and value objects, I think, are also helpful. And so entities are essentially all the different objects in the system that have a unique identity. They have a unique ID, and value objects, again, should be very familiar to us as functional programmers, because they're just, you know, immutable objects that can be swapped out for another instance, and they don't have any particular identity. And probably botched some of that explanation, but these are, you know.
I don't think you botched it.
Okay.
In my experience, DDD practitioners tend to disagree with each other on what exactly is an entity and what it means to have identity.
Yeah,
but,
exactly.
That's
So,
certainly
yeah.
the formulation there. All right. Any other questions? Then thank you again, Marco.
Thanks for having me.
Good. Okay, great. Come on in, everybody. Come and settle down. And we have our first session of contributed talks. Can anybody hear me?
Use this one. This one's fine. We can use it on the board, so it was just muted.
Okay,
That's
fine.
fine.
Yeah. Okay, our first session of contributed talks is going to start off with Wei Shi Ma, who's going to talk to us about F3, which is a compiler for feature engineering. So, take it away.
Thank you for the introduction, and thanks, Michael, for lending me his laptop. And okay, all right. So let's get started. I'm Wei Shi here. This is a work for feature engineering. We built a small language called F3, and it's great to be here. When I first saw the page of this workshop, I was thinking, oh, we should send our work to this place because, you know, functional programming working at Meta is probably a good sign of functional programming working in the large, right? So, okay, this talk is organized around the three questions that you may have. One is, who are you? I think it's extremely important because, you know, when I was looking at any talk, I think usually, you know, how people come up to the solution is as interesting as, you know, if not more than the solution itself. So like people say, when the only tool you have is a hammer, then every problem becomes, you know, a nail, right? So I'm first gonna introduce what a hammer is, and then a little bit about feature engineering and how does functional programming help. Okay, so I went to graduate school at this pretty place called Indiana University, and when I was there, my advisor was writing this book called Little Typer. It's basically teaching high school students dependent types. And and that's kind of the cornerstone of the idea of this work. So I'm just gonna quickly go into dependent type because probably everyone in this room already knows it, right? So, you know, just in ordinary functional programming, you can define this plus, you know, takes two numbers, x and y, it returns a number. So when you write this program, you do this case split, right? So if x is 0, you return the first argument, so on and so forth, right? Next, we can get into the kind of the gateway drug of dependent type, which is like proving plus is commutative, right? And so you can say we have two numbers, x and y, x plus y is y equal to x. Just as usual functional programming, we can do this case split. And here, for the first case, when x is 0, you know, we need to come up with something to prove it's correct, right? So the interesting thing about dependent types here, like as a normal human, when I'm looking at this, I think, oh, so x is 0 here, so probably what I need to prove is 0 plus y equals y plus 0. But actually, that's not what the compiler sees, right? So there is some evaluation underneath going on. So because of the way we define plus, like, you know, if the first argument is 0, then it automatically goes to y, not 0 plus y. So this is not what the compiler sees. Instead, it says something like this. So y is equal to y plus 0. So, I mean, we are still kind of far away from proving plus is commutative, but this is kind of the underlying idea. That is, the compiler sees something else. And this process is called normalization by evaluation, as people already know. And so the idea is, well, there's this kind of syntactic forms and the semantical forms, right? So there are, say, infinitely many different ways to express the same meaning. Some of them can be automatically reduced to a semantic form. Some of them may need some help. But the idea is, well, they all reduce to some semantic form. And when the compiler is doing something interesting, like program analysis, or like for the case of dependent type, it's checking whether two things are equal. But you can do something else. And something else is also based on this normal form. So that's a kind of the start. And next, let's talk about something that people in this room don't know. What is feature engineering? So basically, our compiler serves machine learning engineers. And this is my go-to example of explaining feature engineering to, you know, functional programmers. Let's say I want to teach a class about dependent types, teaching this language called Agda. And I can write a model to predict whether people will like my class or not, right? So this model, it needs to take some inputs. And so I need to come up some kind of signal to this model. So maybe how many lines of Haskell programs my student has written before, like, and then how many lines of induction proofs they have written, or maybe the number 3, do they like Unicode? So anyways, so so those are kind of the inputs. And one option you can do is, all those inputs, they are kind of from some database. What you can do is to dump all this input directly to your model. But usually that doesn't work very well. So what people usually do is to do a little bit massage here. Like, let's say I've been teaching Agda for many years, so I realized, well, maybe the line of code of Haskell and line of code of induction, they are kind of maybe the same thing. So before I giving 2 numbers to this model, I may just add them together and use them as one input. So this is kind of the essence of feature engineering. People just grab data from some database and do some manipulation of data. So as you can tell, this is usually done in a language called SQL. So that's kind of what we have built. All right. So let's see a concrete example. Like, say we have 2 tables. Like table I is a number of induction proofs. Table H is Haskell. And so usually, these data, they do not exist in just one database, not in one table. They exist here and there. So what feature engineering does is to load this many different tables and combine them together. So this process of combining is usually done by this operator called left join, as you can see in line 3, T2. So what this left join does is, so here T0, we call it the main table, because after the left join, all the columns, all the rows still stay in the result table. And this T1 here is kind of the off table. And so sometimes after the left join, the off table, it loses some rows. So maybe, let's say, we have 3 students, X, Y, Z. These are the induction proofs they have written. And this is, lines of Haskell programs written. This poor guy, Z here, just wrote too much Python or C++. And we add them together. So that's, by adding, we join them together. So you now see this new table with 3 columns: name, number of induction proofs, and the number of lines of Haskells. And we add them together, right? So this is a typical feature. And so maybe if I look at this result here, this person Z here, he wrote many induction proofs, but have a huge negative number of lines of Haskell. So I guess maybe since he wrote a lot of induction proofs, he's still hopeful. So what we can do maybe is to add a filter to filter out the kind of noise that impact our calculation. So let's say we just filter out everything that Haskell is smaller than 0. So what we can do is to add another node called filter. So this filter here is saying, okay, so for this off table, this T1, we only want the data where is larger than 0. So let's, for argument's sake, say 50 plus none is 50, but there's something, some other magic we can do. Okay. So this is one way to add this filter. You see, we first filter the T1 table, and then we do this left join. And maybe you can also filter after the left join. So it gives you a different result because, Z now gets filtered, right? So, okay, so this is one problem that we see over and over. That is, we have a compiler that basically transforms the feature in one form to another. So in order to optimize for the runtime efficiency, we often need to move the operators. So maybe sometimes this, and sometimes we need to break down a feature to multiple backend frameworks just for efficiency. So the first thing we need to solve is how do we validate the correctness? Like how do we know if the compiler is, a transformation is not like changing this table to this table? So that's the first question. And so when we have 2 graphs, if they are not the same, we want to tell, well, they are not the same. On the other hand, given the syntax of this, given the semantics of this left one, if we filter on the left table or the main table, it's actually okay to move it, up or down. It doesn't change the semantics; they are the same. So that brings another question. That is, we have a lot of features, like 100,000 of them running on a very frequent basis. So it will save a significant computation power if we can identify the sameness between existing features. So given two random features, maybe we want to identify, well, they do share the same computation at some point in the middle, so maybe we can just compute it once, and then, it saves some petabytes or megawatts. So this is the starting point of this work. One is to check if compiler rules are correctness preserving. The second is to identify the sameness between different graphs. Okay. All right. So as I said, when the only tool you have is a hammer, right? Every problem becomes a nail. So here's how functional programming helps. When I was looking at that problem, this is the exact picture that occurred to my mind. I was like, wow, this is a normalization by evaluation problem. Because you just compute the normal forms of those features or those SQL programs, and then you just check the syntactic equivalence, or maybe some people call structural equivalence of this feature. So that should be good enough. And then the first problem we are going to solve is, well, what does the semantic form look like? So, going back, so this is not a good way to do program analysis because there are just too many layers, just too complicated. We need something kind of flattened, kind of easier to be reasoned about. And so I was kind of thinking it's like a monad if you look at this thing here. So, a monad, it usually has, two parts. The more obvious, more frequently used part because of pure, and the less obvious, less frequently used because of effect. So here, basically, the pure is the columns that each feature provide. Like here, if you look at T3, it's providing, 3 columns, I, H, and N. And also, the effect part is kind of the data range. Like, if you look at this TF, this filter here, it's doing something implicit, like a side effect, right? So basically, the normal form contains 2 parts, the columns and the constraints. Let's see an example, actually the same example. When we are loading this table T0, it provides 2 columns. And along with those column names, we also have how they are computed. For example, this name here, it comes directly from this table I.name, and I is table I.I. And here the constraint is empty. We don't have any filter yet. The second table is equally boring, but the next one, when we do this left drawing, so this left drawing, basically it creates 3 columns, combining the one from T0 and T1. And a little bit trick we did here is if you look at this H here, it's coming from this table H.H, but we added kind of a little tag or some fake function called joined. It kind of reminds us, well, this H here, it was the off table of some left join, or maybe some off table of some left table of some right join. Anyways, it has passes this join, and it's possible that it has loses some rows. So it's different now. And also we added a constraint, which is those 2 names from those 2 tables, they must be identical, right? And the way I look at this, so the column part is kind of like, when you're writing an interpreter, you have this environment or variable bindings, like where does everything come from? Like what are their kind of normal forms? And so when we are computing, recursively going down, like here, this filter here, this T1.h, this H we know is actually a result of join. So in this in the added constraint, instead of seeing table h.h is larger than 0, you'll see this, it's wrapped in this joined tag. And select is kind of the same thing here. All right. So with this normal form in hand, we can just reduce all those programs to their normal forms and just do a simple comparison. So here, if you move a filter, on the right parent of a left join, then you result in a different normal forms like the left and right. But if you move the filter of a left parent, then they basically result in the same normal form. So there are many other different operators in SQL or F3, but they are all handled in this fashion. So basically, yep. So that's the first thing that functional programming has helped, is to identify sameness. So either dedupe or for validation. The second thing, so after we have done the first part, we immediately realize, well, we can use these normal forms for something else, where people in machine learning or SQL, you recall it data lineages and data classifications or labels. So the idea is, well, models, they are effectively black boxes, so you don't know what's going on over there. But those features or those databases, they are the inputs to the models. So if the machine learning engineers are trying to, say, optimize their models, one angle they can use is to look at the inputs. Like if we know all the features, what kind of data is fed into my model and how they are transformed during this feature processing, then maybe it's easier for them to understand what their models are doing, right? So that's kind of the idea. But unfortunately, before we have these normal forms, the features is just a total mess, and it's very hard to connect the data to the models. So, excuse me. All right. So about this data classification problem, we just found a little type system, maybe very handy in this case. So let's maybe start with this expression. So that's something from our last example. So this n here is some table I and plus something else, right? So let's just, so what's its type? What's the type of n? Let's say, class is from two numbers to a number, and join is kind of the identity function. It says n is a number. And this is the least informative type annotation I have ever seen, and it's a number. It doesn't tell you anything at all. And when machine learning engineers look at their features, they also see this, and they have no single idea of what they can do with it. So what can we do? So because in the raw tables, let's say for one, we have name, string, I is a number, and the other table is the same, right? So those are from the source tables. What if we kind of enrich the information we have with intersection types? So let's say for the name, we know they kind of represent some kind of ID, and this I and H here, they represent some line of code. So basically, you can just, people can come up with arbitrary constants as this semantic meaning or labels. So we can use this intersection type to describe something maybe more descriptive, right? So if we have those, then maybe we can run the type inference again, and n is still a number. So why is that? So it's because the way we define our plus function, it takes two numbers and returns a number. So I mean, say we already have subtyping, right? Then number intersects with line of code is still a number, so that's fine, a good input, but output is losing its semantic meaning. So a little trick here, what we can do is to extend our type system with bounded quantification. So basically, instead of saying you take two numbers, returning a number, you can say, well, we are taking now two variables here, A and B. They can represent anything, but they better be numbers. And as a result, we just return the intersection of both. So now we can automatically propagate or infer the information of the columns provided by a feature by using the people, like human given annotations in the table. Okay, let's see. So here on a low level, we know how each column is computed. Here, this table I is what people usually call the main table, and table H is what people usually call the enrichment table, because it's using this information to enrich, to give more information to the other table. So basically, and then on the high level, on a more abstract level, we have some semantic annotations of each column. So using this, we have built kind of a database or knowledge graph or whatever you call it, so people can query all existing features. Like if someone is trying to write a new feature and they want to use this table I, so they can go ahead and query the existing, say, 10,000 features and ask, okay, so what other columns are usually used together with this table I.I? And we can return some information saying, maybe you want to use this table H because other people are using it as well. So that's one use case. And the other use case is we can check if people are using the columns they are not supposed to use. Let's say if someday this line of code becomes illegal to be used in some country, then we know, okay, so this is a feature that we should not run anymore. Okay. All right, so that's it. So using this, I know it still doesn't look very neat, but at least you can trace where each model have their signals coming from. So that's what we have done. Okay, so in conclusion, functional programming works very well in the large, and so we built this little Python DSL, and yeah. Okay, that's it. Any questions?
I'm curious to understand a little bit more about what's the distinguishing feature set of this DSL, and kind of what are the surfaces, what are the features you're trying to surface to the feature engineers? Mm-hmm. So it sounds like on some level it seems like, it's like a SQL engine. Mm-hmm. And I'm curious, like, is it like, how close is this dialect to SQL? Does it have like, is it importantly like different in its expressivity? Mm-hmm. And like when you're doing feature engineering, like examples of like interesting things you have to do, sometimes you have to deal with temporal features where you're like talking about the evolution of some signal over time, and you want to like include like distributional properties of the feature, so like you can like normalize them by their distribution. I'm curious if there's any of that kind of stuff here. Mm-hmm. And I'm also curious like how much of the kind of like optimization and analysis of this is kind of just what I would find from like a query planner in some other SQL dialect.
Good question. Thank you. So first, this project started as kind of a small extension of SQL. One motivation of making this DSL, I guess, was to have machine learning engineers write Python, which is considered better than writing SQL or C++, I guess, back in the days. And then gradually, we also discovered many use cases of feature engineering that are not SQL-ish. So there are some new computation paradigms, like you can actually invoke a model, or you can do some graph learning during this SQL engineering. So it's gradually growing out of SQL. So that's first question, I guess. And this is only part of the syntax. And also, I guess your second question is, there are many features. Are most of them just temporary, right? Or
this is a kind of about the expressivity question of like, how much time-oriented stuff do you have there? So you can do like, I guess the two features that were striking. One is asking things about the history of stuff and whether there's any special support for that, and then also distributional properties. Like sometimes you want to normalize a feature by going from its looking at its standard deviation, and then like adjusting it to some, I want to pull things within some small, so that like within 2 standard deviations between 0 and 1, because like ML models, like neural nets, are often like tuned to particular numerical ranges, and so sometimes when you don't just want to, all of these examples are like transforming like row by row, but sometimes you want to do transformations that have to do with an understanding of the full distribution of the data. And I'm curious whether any of that shows up in the DSL.
Yeah, good point. So first off, that's something we haven't started yet, but that's a very good point. And I guess since we have these normal forms, we also have the data range. And like something's larger than 0, we have those constraints. So yeah, I think it's possible to do that, and maybe. Yeah, we can definitely calculate some kind of distribution by using those constraints. But I guess eventually it's not a static problem. It's probably you have to run those features anyways to get the actual data, and in order to get an accurate estimation, I guess. Interesting question. Thank you.
If I understood correctly, you wanted this to, well, practically speaking, what are the benefits that people want out of it? One is, if I understood correctly, to share some of the computation by realizing that you keep doing this over and over for different features. So I guess, could you show us some performance benefits that this has led to? How much did you gain out of this?
Yeah.
And the second thing, I didn't understand the part about trying to clarify where the models come from so that the modelers know. Is that just something that they use heuristically to figure out which types of features seem to be useful, or do they do another optimization step over the types of features that they ask from you?
Sure. I guess I can answer these 2 questions together. So about the result of optimization, we do see great gains in the units of megawatts and the petabytes. And for example, maybe we are maintaining a lot of databases, say, on the left-hand side. And if using this lineage tracing, we identify that there are some tables that are not actually used by any models, then maybe we can just deprecate that and save some storage space. So that's one thing. And the other is definitely you have many features that you identify the duplicate computation and to save some electricity to compute them. So does it answer your question?
I guess I was interested in what percentage of the cost does it, like, did you
do
any measurement of it?
Yeah, I think I saw the number somewhere. I don't recall the numbers right now. Let me think about that and get back to you.
We've got plenty of time, so.
Just a quick follow-up. It looked like maybe the normalization step would do query optimization, or do I misunderstand?
Yes.
So that would be also a optimization benefit, efficiency benefit.
Sorry, can you ask your question?
So the normalization would produce a more efficient query to the database. So that's also a gain from the system.
So we just store the normal forms of these features, say physically somewhere. And when someone tries to understand the features, we just query those.
I've got one. What's the biggest remaining pain point that this doesn't solve for you?
So the biggest, so this compiler project started a long time ago, and when it was designed, it was, another benefit of functional programming I should brought up is pattern matching. Like Currently, most compiler rules are still written in this form of graphs. So basically, the IR, the intermediate representation of the compiler, is kind of like a C-ish or Python-ish graph. You first have this graph node, and in the node you just embed an operator. Inside the operator, you embed some expressions, and so it makes each compiler rule. I mean, to describe each compiler rule, you just write a lot of code. And so because you have to find the graph and find the relations, unbox the node, and then put the box back, something like that. So one thing we are trying to do now is to make it more functional for the internal compilers. So like we just do pattern matching, and so one line can solve a problem 100 lines. So that's kind of the major project we are thinking about. Thank you.
Okay, so we'll take a short break now, and we'll start again at 11:45, as per schedule.
Can I plug in mine?
Yes, that's fine.
I need the sharing is not sharing the. Maybe this is an adapter. Maybe we can. Was there?
Yeah.
Maybe we can try this one.
Okay.
Okay. Okay. Maybe.
All right.
Okay.
Well, thank you so much.
Oh, you're welcome. Okay. Should be. Maybe you can.
Good morning, everyone. So today I'll be presenting our work on design and implementation of a verify interpreter for additive manufacturing programs. So let me start by explaining what additive manufacturing is. To do so, I will draw a contrast between conventional manufacturing and additive manufacturing. Conventional manufacturing falls under the category of subtractive manufacturing, where parts of the tools are removed. Some examples of conventional manufacturing are milling, lathe, and drilling. Additive manufacturing, on the other hand, deposits materials layer upon layer in precise geometric patterns to create tangible objects. And since there is addition of material going on instead of removing the parts, it's called additive manufacturing. And there are typically 7 types of additive manufacturing techniques, namely material jetting, wet photopolymerization, binder jetting, material extrusion, directed energy deposition, sheet lamination, and powder bed fusion. In this work, I'll be discussing the material extrusion, wherein material or the filament is extruded from the nozzle and melted to synthesize a 3D-dimensional object. Just like any physical processes, additive manufacturing also has different sources of errors, which are classified into 3 categories. Software error, where errors can arise in the toolpath planning software. Errors can come from the post-processing software as well. Kinematic and geometric error, which includes errors coming from collision between the printer head and the object being printed, and the thermally induced error. Configuration error.
Can I just ask a quick question? I didn't quite catch you mentioned extrusion.
Yeah.
You're going to fix it, but I didn't really quite catch what it was.
Oh, sorry, yeah. So extrusion is basically the technique wherein filament is, it's a finite deposition printing. So a filament is extruded from a nozzle, and then you heat the filament and melt it, and then you deposit it in a pattern which is specified by the CAD model. So yeah, material is extruded, and then you heat it, and then.
So is that related to? I guess this is obviously a lot bigger than 3D printing, but is 3D printing an example of that one?
Yes, it's a finite deposition.
Right. Okay.
Yeah.
But it could be other materials.
Exactly.
Right.
Yeah. So 3D printing is just one type of material extrusion.
Right. Okay.
Right. Yeah. Good. Yeah. So the third category of error is the configuration error, where the errors can arise from human errors in specifying coordinate information, or incorrect specification of tool offsets and fixtures, or poor selection of feed rates, spindle speed, or unwise choice of the order of machining. In this talk, we'll be focusing on just the errors arising in the toolpath planning software. So there are 2 common approaches for validation in additive manufacturing. Those are simulation with visualization, and physical examination of the artifact after fabrication using destructive and non-destructive testing techniques. And each of these techniques have their own set of limitations. For example, the visualization can detect issues that arise from incorrect rates or temperatures that can affect material properties, or you can not even track the errors due to uncertainties during the print process in the simulation processes. And as far as the high fidelity physical testing is concerned, it's very expensive and time consuming. So essentially, these 2 approaches are kind of expensive, and imagine like you have printed the entire object and then you realize that it doesn't meet design specifications. So you have wasted all these resources. So we want to develop some techniques which directly analyzes the tool path. So we have started looking at the toolpath software verification, and in our literature survey, we haven't found any prior work in toolpath software verification. And just to give you a feel of where this lies in the whole 3D print design cycle, I'll be discussing the cycle here. So first, you create a CAD model of the object using a design software like AutoCAD, SolidWorks, or Maya 3D. And then this object files, this object files or the STL files are then imported to a slicing or toolpath planning software like Ultimaker, Cura, Slicer, or Simplify 3D, which then generates a set of instructions called the G-codes, which are then fed into a 3D printing device firmware like Marlin, Clipper, and RepRap, which uses this G-codes to print the 3D object. So as you can see, like there are these boxes which specify the stages, and theoretically each of the software components can be verified using traditional program verification techniques. In fact, there has been some prior work in the PL community by Chandrika Nandi and her colleagues who have looked at the design software phase, wherein they have developed this programming language called Lambda CAD, which synthesizes like a geometric design. But still, there is a major gap in the stage between the slicing and the 3D printing device firmware, which we have indicated using this red arrow. And this particular stage is very important because these are the actual machine instructions which go to the firmware for printing. And there are potentials for tampering and corruption which can lead to, which can disrupt the integrity of the print. So this is a very important stage that needs to be analyzed to maintain the integrity. So with this motivation in mind, the goal of our work is to detect whether the command sequence that drives the printer introduces subtle defects like misaligned extrusion or incorrect dimension. And the approach that we use to achieve this goal is to develop a direct interpretation of the G code such that the verification conditions which enforce some domain-specific constraints in the printing cycle can be checked at each step of the print as the machine state evolves. So the operating word here is as the machine state evolves. So we check, during the whole evolution cycle. And to ensure that the bugs in our tool doesn't cause us to incorrectly verify a G-code program, we have taken a verified software approach where we verify every component of where we verify the core component of our analyzer, so that we have an absolute guarantee that whatever we are analyzing about the G-code is correct. Now this approach of doing toolpath verification is not very trivial, and to explain why this is not trivial, I will draw some parallels between the traditional program verification and additive manufacturing program verification. So in the traditional program verification realm, where we want to analyze some properties about, let's say, opaque compilers, we cannot directly do so because we do not know what the semantics of the compilers are. So it's not exposed to us. And in that case, what we have to do is we have to resort to some other kind of analysis called the binary analysis, where we analyze the output of the compiler against a semantic model of the machine. Similar problem arises in the additive manufacturing realm as well, where we do not know what whether slicing and printing software is opaque, and as well as the 3D printing device firmware is opaque, which is the case for most commercial 3D printers. So in those cases, we cannot directly apply program verification techniques, and we have to resort to and we have to develop some analysis similar to binary analysis, where we analyze the output of tool path planning software, which are the G codes, against a self-defined semantic model of the firmware. And the reason that I focus on self-defined is that, again, the formal model, semantic model of the 3D printing device firmware is not available. It's pretty, I mean, they have done it in a very ad hoc manner, so we have to mechanize or define this semantic model. Fortunately, most of these firmwares, they follow the standard called RS-274 standard, which was initially designed for traditional manufacturing and a subset of that has been later adopted for 3D printing. So we'll be looking at that particular standard or the particular style of writing programs for manufacturing. So next I'll be discussing what this RS-274 standard is. So the RS-274 or the NGC language is based on a line-oriented execution model, where each line include commands that can to perform a task like move the printer head in a circular arc or in a straight line while extruding the filament. And the words for these commands are called the G or the M codes, where G codes mostly operate on the physical state of the machining tool, like move it in linear motion or directed circular motion. And M codes mostly operate on the controller state, such as turn on or off the coolant or select the extrusion mode. So on the left-hand side of the slide, I have presented an example of what this RS-274 language looks like. So as you can see, these are a set of G instructions followed by some axis commands. So let's look at the first example where we print a square. So let's assume that the printer head starts from the origin of the coordinate system 0, 0. Now when we instruct G1 x 1.0, what does is that it tells the printer head to move 1 unit in the x direction in linear motion. So G1 stands for linear motion. So each G command has its own specific meaning. So here, so then the printer head moves to 1, 0, then G1 y 1.0, then moves the printer head to the coordinate 1, 1. G1 x 0.0 moves it to 0, 1, and then G1 y 0.0 moves it back to the origin, which is 0, 0. So we have traced a square path. And as you can see, this G instructions, the G commands have caused the machining center to change from one mode to another. In this case, it's the physical mode. There are other commands which also lead to change in the controller state. And these commands are typically classified into two categories, modal commands and non-modal commands. So for the modal commands, some modes may remain active until this modal commands change it explicitly. Like for the example of these modal commands are G90 and G91 for absolute and relative motion. So if I go back to the example of the square, we have this G90 and G91 on top of the program. So what it does is that G90 says that the printer head should move in a coordinate system which is absolute or attached to the printer bed, and G91 stands for relative distance mode, which says that the motion of the coordinate of the printer head is with respect to the reference attached to the printer head. So essentially we have these two different distance modes, and another point to note is that we just write G90 and G91 once on the top of the program, but there is an implicit G90 attached before G91. So if you write it explicitly, it would look something like G90 G1 x 1.0. So this G90 command is active throughout the program, and that is why it's called modal command, because it is active even outside, even after the line that it is specified. And this will remain active unless we say G91. So when we say G91, then the modes goes to relative. So essentially, yeah, we have both this G90 G91 remain active until either of them is specified explicitly. On the other hand, we have the non-modal commands whose effect is restricted to one line, to the line in which they occur. And yeah, so outside that, we do not have the effect of these commands. Now the modal commands are further arranged in modal, yeah?
So do these G codes, they only specify the location and don't specify the speed at which to move to the location?
So the speed is specified by another code word called F. So that stands for the feed rate. So it says that at what speed the printer head should move when the material is extruded. So you have other G commands and F commands associated with the speed. Yeah. 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 So these modal commands are arranged in modal groups, and these modal groups are pretty much independent of each other. So that means is that transition in that modal group will not affect the state of any other group. So on the left-hand side of this slide, I have presented two modal groups. One modal group is for the distance mode, and then the other modal group is for the feed rate mode. As you can see from the state transition diagrams, both the state transition diagrams are self-contained, and there is no transition from feed rate mode to the distance mode, so they are independent of each other. And the other thing about these modal groups is that some modal groups have a default G-code value. For example, the distance mode has a default G90. So what that means is that when you turn on the machining center, even if you don't specify G90 or G91, by default it assumes that the distance mode is G90. So all the motion of the printer head is now with respect to this absolute coordinate system. On the other hand, modal groups like the feed rate mode do not have any default G command associated, so it remains inactive if nothing is specified. And to say what kind of mode you want, you have to explicitly say G93, G94, or G95. So as you can see, like there are a lot of subtleties associated with how the modal commands transition from one mode to the other, and yeah, so we capture all of this in our interpreter using a state model. So here we track two states: the physical state, which was the position of the printer head, and then the modal state, which determines how the modes transition, and all of this are grouped into a machine state. So we have defined this using a record in Coq, which tracks both the physical and controller. So this machine state can be decomposed into physical and controller state, where the physical state contains parameters like the position of the printer head in absolute coordinate system and in the relative coordinate system, position of the extruder and whether the extruder is on or off, and also it tracks the path of the printer head throughout the printing process. The controller state, on the other hand, can also be decomposed into a physical state and a polymodal state, where the physical state determines what kind of physical parameters are associated with some of the G codes. So if you remember the example of the square, we had G1 x 1.0. So that means that that x 1.0 was the physical access parameter associated with that G command, and that forms the controller state. And there are similarly other kinds of physical parameters like coordinate offset, like between, let's say, G90 and G91, and then G93, G94. So all those transitions are tracked by this modal state, and it also maps a mode in a modal group with associated G commands. So as you can see, we have this clean separation between the physical and the controller states, which was really essential in the design of a verified interpreter, because when we started with an initial prototype of the interpreter, which was a monolithic OCaml code implementing all of this in one machine state, it created a lot of issues with respect to verification when we wanted to use different tools for different parts of the interpreter. So this nice clean separation introduced a modularity, which was very helpful when we started doing the verification process. So next I'll discuss the high-level interpreter design. So our interpreter takes as input a G code and then parses it into an AST by following a priority order for evaluating the commands. And this is very essential because if we do not follow a priority order, then it essentially leads to a misinterpretation, and the whole thing goes, it just blows up. So once we have this normalized, AST, which is normalized according to this priority order, we then pass it, we then define an interpreter step function, which is implemented and verified, and therefore forms a part of the verified core. And this interpreter step function walks through the AST and then executes the command sequence and generates an output state. This output state is then fed into the VC checker, or the verified condition check, which is also forms the part of the verified core. Now this VC checker, what it does is that it enforces domain-specific constraints, like the machine state is inside the bounding box, and if this output state satisfies this VC check, then interpreter step function steps through the next command sequence, and the process repeats until we reach the end of the file. And if this whole thing goes well, then our interpreter emits a execution trace, which essentially tracks the coordinate of the printer head throughout the print, which can then be exported and visualized to visualize the 3D model. However, if at any step the output state doesn't satisfy this VC check, then the interpreter terminates and it generates a failure report, which essentially details where things have gone wrong, and it has a very helpful message. Salient feature of our tool is that it's modular, which allows us to integrate more complex verification checks without impacting the rest of the interpreter. So, for example, let's say you want to write a VC checker which does the collision detection. Then you can seamlessly integrate that with our tool and without impacting the rest of the interpreter. And this gives a nice like modularity, and you can compose things together. Yeah. So next I'll be discussing some of the challenges or the barriers that we identified during our verification process. As I mentioned earlier, we started with a monolithic interpreter, so that was verifying that was challenging because we could not use different tools according to the strengths to verify the interpreter. So we had to decompose the physical and the controller states, and then this nice modularity helped us to verify parts. So once we achieved this nice modular design of the interpreter, we started verifying, and there were some specific challenges. The first challenge was with respect to I/O and parsing, which was notoriously difficult to model because the RS-274 standard does not provide a formal grammar for these G-code programs. So we had to carefully go through the manual and write the grammar. But we did not verify it yet. We focused our attention on verifying the core interpreter. And since these are not very critical, this formed the distributed computing base. The second main challenge was that we started using these tools, Chameleon and Gospel, which do direct verification for the OCaml programs. But soon we ran into the issues that this tool Chameleon does not handle functized maps and has no floating point support. Furthermore, the Gospel, which is a specification language for OCaml, only handles a very small subset of OCaml and was not well suited for verification. So we had to move from direct verification to an indirect verification approach, where we used tools like Y3 to write parts of the interpreter in YML and then extract it out to OCaml. Furthermore, there were some issues with Y3, specifically with respect to floating point reasoning and extraction, which forced us to use tools like Coq to model the physical part of the interpreter. So what ended up happening was that we had to use Y3 and Coq together, and this nice diagram on the left-hand side shows how this dependency looks like. So the main property that we verified here is the correctness of the interpreter step function, which relies on a set of core libraries like logical operations, maps, and data structures, which model the modal states. And this maps and these green boxes were were the ones that we have verified in Y3, which models the model state. And then the yellow boxes, which includes the floating point operations and linear algebra operations, which track the evolution of the physical state, was verified in COG using the flock library. And once we had all of these structures verified in Y3 and COG, we extracted them out in OCaml and then integrated with other parts. So next I will dive a little bit into verification in both Y3 and COG. So I'll start with Y3. So as I mentioned in the previous slide, for the Y3 we have verified properties about the model states. Here as well we had some challenges. The main challenge was that when we wrote our first design of the tool, it used functorized data structures like maps and sets to model the modal states and the transitions between the modal states. But Y3 has very limited support for verifying and extracting this functorized data structure, so we had to restructure our design and use the primitive structures like lists, which are easily verifiable in Y3. And this posed a trade-off between verifiability and performance. Fortunately, the list of modal states that we maintain have a small example on explaining how the verification in Y3 is done. So in this example, we write this function which verifies the membership of a string in a list. This list you can think of as a list of non-modal commands. So the properties that we verify about this string membership function is that first that this function terminates, which is easy to verify using variants. It is in this variant clause which verifies termination of the variant clause on the list, because and since the list is a finite. Since we have a finite list, it's easy to verify by structural recursion on the list. And the second property that we verify is that the result from the string membership function indeed satisfies the mathematical definition of membership, which is defined using this mem predicate in the YML standard library. And once we have verified these two properties, we then extract the YML implementation into OCaml and then integrate it with other parts of the interpreter. So this is just one thing that I have shown. There are other stuff about how modal states are modeled and what kind of properties that evolve, which is a little bit more subtle than this. And the other thing, so the Y3 was about the modal states. Now we have used COG for verifying properties about the physical states, where we so in this case as well, when we started doing the verification, first we wrote our floating point operations in Y3, and then we tried to extract out the Y3 implementation to OCaml, but we ran into the issue that Y3 does not support extraction of floating point literals, and that was a major issue because we use floating point literals throughout our interpreter. So we had to abandon this Y3 approach for floating point arithmetic and then move to COG. Where we use the primitive floats in COG and extracted them to OCaml and use the flock library for verification. So in this slide, I have shown like a small example on computing the dot product of two vectors. So we define dot product in COG, we extract it out to OCaml, and the property that we verify about this dot product is that the dot product is finite, and we use the flock library for that, and we verify this using an assumption that the dot product doesn't overflow and each element of this vector is finite. So we use this example here is very simple, but we have used a similar approach to verify some other complicated properties about the linear and the circular motion of the printer head. So to summarize, so far what we have is a verified core library of the data structures and the linear algebra operations, and we have extracted them out and to get our verified interpreter. But there is another part, which is the main driver code written in OCaml with effects. And challenge was the next challenge was how we propagate these effects throughout our core interpreter. And to do so, what we did was we modeled the effects in COG using monads. And one specific issue there was that we started with a generic type class definition, but we found out that this was not well suited for code extraction, and therefore we had to define a specific instance of the monad which models the intrinsic behavior of the effects in this additive manufacturing programs, so that we can tightly integrate the verified interpreter code with the unverified driver code. And by doing so, we achieved like a whole tool with verified and unverified components. So next I'll be discussing some results. So the first result that I would like to point is the number of lines of verified versus unverified code. So about 54% of the code base was verified in Y3 and Coq and extracted in OCaml. And the remaining 46% was handwritten and includes the G-code parser, JSON parsers from configuration files, boot output functions, ASC generators, and petty printers. And we have tried to write them down as much as possible without depending on the third-party dependency, because eventually we want to verify them and minimize the trusted computing base and get more of the verified code base. If you look at the table, the other thing that you might notice is that the number of lines of extracted code in YML is much less than Coq, which means that we had to do a lot of manual verification. But that was because of the limitation of the library in supporting, especially the floating point arithmetic. And we communicated that with the Y3 developers, and they said that they will try to resolve the issue in the next versions of Y3. So once that is up, we plan on migrating as much of the code to the YML so that we can get more automation out of that. So the second result that I want to highlight is the results from the verification condition checks. So if you remember, in the high-level interpreter design, there was one box in the verified core about VC checker, which verifies some domain-specific constraints for the output state of the interpreter. So that we have currently in our prototype tool, we have two verification condition checks. One which says that the printer head is always inside the bounding box. So we check that the coordinate of the printer head is always inside the bounding box. And the second condition is that for the arc motion, there is no trajectory such that the printer head will ever be outside the bounding box. In this case, we do not explicitly compute the coordinate of the printer head. Using the input G-codes and some of the complicated vector calculus that we have implemented, we predict whether the arc motion will leave the bounding box. And to demonstrate the feasibility of that, we have these two nice pictures where we show the detection of this arc motion violation for the bounding box. So what we did here was that we took a G-code command which prints a circular motion. So in the first figure, you have the whole arc inside the bounding box, which is represented using this blue trace. For the violation, what we did was that somewhere inside the G code, we inserted G91, which changes the motion from absolute to relative mode, and therefore after that G91 instruction, everything was all the motions were done with respect to relative frame of reference, and the coordinate updates due to that led the arc to go outside the bounding box, which is highlighted in this using this red trace. So the red trace essentially shows the toolpath that is outside the bounding box. So in this way, we have tested some of the G codes for the violation check detection. And the third main result that I wanted to highlight was the visualization of the 3D print itself. So in this case, what I did was that we took an STL file for a VAS, and we imported that in this classing tool called Ultimaker Cura, the visualization of which is shown on the left-hand side of the slide. So this Ultimaker Cura takes this object file, it slices into a G-code instruction, which is then fed into our analyzer. And the result on the right-hand side is the visualization of the path trace of the 3D printer that is emitted from our analyzer. So as you can see, like there is we have captured the whole design that was initially fed into an analyzer pretty neatly. And the best part is that all of this, like the code interpreter is verified, so we get this nice result from our verified analyzer. And the other thing that I wanted to highlight here was that which is a strength of our tool, is that we capture the whole tool path motion, which allows us to do some complicated bases. So if you look, if you look at the diagram, there are two color codes. One blue, which says that which indicates the actual extruded material, and then there is also a red trace, which shows the tool path motion without extrusion. So we capture both the extrusion and the non-extrusion tool motion, and by doing so, we get like the full tool path motion, and then we can do some complicated PC checks like collision detection and those kinds of stuff, which is.
Could you look at the screen?
Oh, right, sorry. Yeah. So in this.
Go to the screen.
Okay, sorry. Yeah. So essentially, this dots were originally like red in my computer. So these are actually the motion without extrusion, and this nice greenish color is the extruded part. full-fledged deep analysis on the tool path planning part, which is not well supported in the simulation-based approaches. Yeah, so since we are at the FUNARCH workshop, so we have derived some of the architecture lessons from our experience. So the first lesson that we have derived from our experience is that modularity helps a lot in doing the verification. The fact that we were able to decouple physical and controller states allowed us to do verification using different tools like Y3 and COG. If one were to use some other tool, they can plug that in and do the verification because of the nice modular framework of our tool. And the second lesson was that at some point I've mentioned that we moved from functorized maps to the list-based maps. So in that case, we have we favored verification over performance and use structures which are amenable to verification. And the reason that we were able to do that was that we did some evaluation of the performance differences, and we found out that it was not too high. And similarly, like if you go beyond beyond the additive manufacturing into some generic function programming, where you face a similar kind of trade-offs, if the performance difference is not very high, then it would be nice to use data structures which are more favorable for verification. And the third thing was that we try to reduce as much of the third-party dependency as possible and write as much of the code on our own. So just to give you a little bit, to give you numbers, we have like about 60 lines of 110 stream parser and 100 lines of parser commenter library, and which we eventually want to verify. And by reducing the third-party dependency, it allows us to do verification without having some additional challenges. The next major architecture lesson that we learned was regarding modeling effects. So here we evaluated the generalizability of modeling effects and tried to leverage as much of the inherent behavior of the system by developing a specific instance of this monads to propagate effects, which allowed us to smoothly interoperate between the verified and unverified components. And this is something that often comes up in other functional programming projects as well. To conclude, the primary focus of our work was on the design of a verified interpreter for additive manufacturing program, and we achieved that goal by focusing on decomposing the machine state into physical and controller state to facilitate modular verification. And then in the end, we highlighted some of the architecture lessons in generic functional software design. In terms of the future direction, we have started looking at some of the, we have started pursuing some of the directions, and some of the directions are something that we have will be focusing on in near future. So the first direction is implementing some complicated verification checks like collision detection using KD trees data structure. So we have implementation of this KD data structure in OCaml, and we plan on mechanizing that and integrating that with our tool. The second direction that we want to pursue is about modeling uncertainties. So uncertainties can arise throughout the print cycle. It can come from the motors, from the discretion with the motors or other physical noise, and to get some accurate guarantees on the error in the printing process, we want to model these uncertainties, and that's something that is on the near horizon. The third thing that we want to pursue is implementing some vendor-specific extensions to G-code for 3D printing. So this these commercial 3D printers, they come up with some vendor-specific extensions, and to make our tool generalizable for analyzing the output of those print process, we want to model the behavior of these extensions. And the fourth direction is automating as much of the proof process as possible, preferably by developing some high-level program logic for this 3D printing process based on what we have learned during our mechanization of the G-code semantics. With this, I would like to conclude, and yeah, thank you everyone for listening to my talk, and yeah, I'm happy to take any questions. Thank you.
Thank you, James Chapman, Input Output. So I think I've got a couple of questions, but so one thing I was wondering about was the kind of correctness property that you're proving. So you talked about I saw that you had you showed an example of a small component, and with a correctness property for that it was correctly capturing list membership, I believe. So that obviously gives you the that each of the smaller components are well built. But what's the high level property?
Yeah, so the high level property is that like for the given input state that an interpreter step function takes in, we want to say that we want to say that the invariance. So there are some invariants, like there are modal state invariants, which talks about how the modal state update needs to behave, and then there are some physical state invariants, like at every step, the vector that we get, the physical vector for the coordinate, is finite. Like we do not get any nans or any infinities, etc. Like some exception for important values. So with physical state invariants, we maintain that all of the resulting vectors, like at every step, the state has those finite values. So those are the kind of invariants that we want to maintain both for the input and the output, and that's something that we verify. And the second thing that we verify is that is about the parameter handling process. So if you remember the square example, we had G1 x 1.0. So a value, so that's a valid G code. But let's say you just mentioned G1 and you skip the x 1.0. So that is an invalid G1 command. So those are some of the properties that we check as well, correctness properties. And then when you make state transitions, you would want them to be contained inside the modal group. We do not want any transition from one modal group to the other modal group. So those are the kinds of behavior that we want to capture in our correctness property. Yeah.
So I'm wondering if this approach is also applicable to subtractive manufacturing, because I think subtractive manufacturing is a lot more, I would expect it to be more difficult than additive manufacturing.
Right. I mean, both subtractive and additive manufacturing, they have the same style of writing. So the NGC, ISO74 NGC language, that same language is also used for the conventional subtractive manufacturing. So this analysis can also be extended to subtractive manufacturing, because they have the same flavor of writing. And even the G code means, like some of the G code have the same semantics for both conventional and additive manufacturing.
Yes, but I'm not sure. I guess with additive manufacturing, it's typical not really a problem that your printhead, in this case, will bump into the object that you're printing.
I mean, there is a possibility that it can happen.
Okay.
Yeah.
But
For
is
example,
that...
like, if you do like a rapid motion from one point to the other point, it can happen that
that's true.
The rapid motion it's not like it goes in linear motion. It can go like zigzag in any fashion, and it might happen that it can bump with the object in that case. So there is a possibility that there is a collision between the printer head and the object.
Okay, thank you.
Yeah, thanks.
One thing I was wondering is, it's interesting that you didn't find any prior work about taking a software verification approach to this kind of problem. But I think there is quite a bit of prior work about software verification of plans for robotic arm movements and that kind of thing.
Right.
And I wondered whether there were interesting similarities or things to be transferred between the fields there. Did you think about that at all?
Yeah. So yeah, I mean, there are some similarities, except that those arm motions. So here we are targeting like a specific style of the language, which is this ISO74 language.
Yeah.
So so here essentially our front end was like this particular language, and we developed our interpreter for that language. But then there are some similarities about how transitions happen, which can be extended to the arm motions as well.
More questions?
So one thing on your motivation slide, I thought you said that you can't verify a compiler. I mean, surely not, right? So you said sort of traditional program verification, but there are things like CompCert. So maybe I must be missing the point. So CompCert, being a verified C compiler, and there are other approaches where you can take a grey box approach, and each compiler step would output an abstract syntax tree, and you could check if it's doing the right thing. So, yeah, I thought I must be missing something.
CompCert try to model the
Okay, and I guess, of course, I mean, when they designed ComCert, they started from scratch. They didn't take something like GCC and then try to verify it after the fact. So, yeah, okay, interesting.
Yes, I have another question. I was wondering, so my background is in, well, runtime verification, and I was wondering if there's effort, not necessarily with your research, but in general, if there's an effort in actually trying to check if the machine at that specific moment is still doing what the G code describes. As in, continuously check that it's not, steering away from what the G code describes the machine should do. Okay, thank you.
Thank you for the talk. You said that in the RS-274 that it didn't provide a grammar. Can you describe, was that a problem for you, frustrating in any way, or were you able to kind of reverse engineer it yourself?
That ties into the last question I wanted to ask, which was also about the standard. So given that the standard has this ambiguity, have you considered either proposing to update the standard or come up with a new one? I mean, if it's an ambiguity, perhaps it could be a sort of more minor update, or maybe there are other things that could be improved.
Any more burning questions? We've got 2 more minutes before lunch. No? Well, let's get a 2-minute advance on lunch then. Thank you very much.
Thank you.
I'll be with you at 2.
shame you couldn't. Yeah. This paper came out of a sort of lively conversation.
So, welcome back after lunch. Now we're going to hear about formal methods at input-output. Can you clarify, is it now input-output global or Hong Kong?
Yes, so
what's the branding like these
we're
days?
Going through a rebranding exercise at the moment.
Okay.
So, yeah.
Anyway, so applying formal methods to the Cardano blockchain. Take it away.
Thank you. So, hello, I'm James Chapman. I'm head of formal methods at IO. So I'm going to talk to you about applying continuous formal methods, which is the name of our formal methods strategy, to Cardano, the blockchain. So the paper is joint work between me and so I'm a formal methods person, and Arnaud, who's an architect, and also a very hands-on architect. So he's also kind of he's also a developer as well. And Polina, who's a formal methods person, but also she's worked in research. And all three of us have a research background. So I think we're sort of covering sort of engineering, research, and formal methods, and how to kind of integrate those here. And of course, I should say that this is based on joint work with a great many people, all of the engineers within IO, the rest of the formal methods team, and the researchers. And yes, and two of my colleagues, Kevin Hammond and Luta, are here. So if you would like to talk to them, feel free. So I'm going to, just to give some context, I'm going to say a little bit about the company, about Cardano, our approach, the continuous formal methods approach, and about how we've applied it to the Cardano node. That's the software that people are running on the internet to support the network. And so I'm going to give some case studies there, and also how we apply it in innovation R&D, so bridging the gap between research and development. And then, as this is an experience report, I'm going to reflect on the challenges we face, and how we meet those challenges, and also how we've kind of refined our approach. And then at the end, I would like to advertise a couple of things. Okay, so I'm going to start with the company. So input-output. So we are a blockchain R&D company. We were founded in 2015. We have about 500 people. We have quite a big research department and research connections. The high-level ones, I think, really are with Edinburgh, Stanford, and Tokyo Tech. But we have lots of other kind of direct and very effective research collaborations with groups or with individuals. So we have quite a big, lots of research connections, and we put a lot of work into research. So we've written around about 200 papers. We're also kind of a big part of or we support the functional programming community. So we support the Haskell Foundation. We've been involved from an early stage with that. We support JFP. We are sponsoring types. We have a booth if you'd like to come and talk to us outside. And we also sponsor other academic events such as types and the Agda Implementers meeting. And we are the company that built the Cardano blockchain. So let me say a bit about Cardano. So to me, the aim of Cardano is to be the world's financial operating system. And actually, in an earlier talk, there was a reference to, which made me think about this. There was a reference to the Little Typer book. And I reviewed that book. I think my name is somewhere in one of the early pages, so I hope I'm not de-anonymizing myself. But I reviewed it, and MIT Press kindly sent me a rather small fee for the work, and they sent it to me as a check in US dollars. So it took quite a while to arrive in Glasgow, and then I haven't had a check for a while, so I kind of thought, oh, I've got to go to the bank, and then I went to the bank and it was shut, and then a couple of weeks later I managed to go to the bank and it was open. And first of all, they tried to send me away, and because they tried to get you to do things on your phone instead of actually going into the bank. So got through that, and I gave them my check, and they looked a bit puzzled, but I thought it's from MIT Press, and it looks like a very recognizable US bank. I thought they should be able to deal with it, but it took a very long time, and a sort of a month and a bit had passed, and then they sent me a message saying that it wasn't the kind of standard check, and I was thinking, I think it's quite a well-known bank, but anyway, eventually I got my small fee converted into pounds and into my bank account after they'd taken a rather large fee, and it took several months. So I think this is a nice example why it'd be nicer to have a world financial operating system, and also having got mortgages in 2 countries, I think having these kind of some financial history which is transferable would also be useful. Anyway, moving on back to Cardano. So Cardano is the number 11 cryptocurrency by market capitalization. It has a daily volume of around about $200 million. These are some figures I looked up the other day. It's really rooted in research. So one of the foundational things is the Ouroboros consensus algorithm. And as I said, we've written a lot of papers, and as I go through my talk, I will sort of highlight connections with papers or where we've written papers about what we're doing, or papers have been an input into what we've done and how we've done it. It's written in Haskell and formalized in Agda. This is a little bit of an oversimplification, but I think it's reasonable. Of course, there are specialist bits that are written in languages other than Haskell to do with cryptography, and there are other things that we do beyond Agda. It's proof of stake, so it doesn't use enormous amounts of electricity like Bitcoin, and it's based, as I said, on the Ouroboros consensus algorithm, which has really been a competitive advantage, and is something that has had widespread adoption in other blockchain systems. And that's some research that is centered in Edinburgh. It's built by IO, and I've missed somebody off here, so so it's built by IO, and we work closely with Twig, Well-Typed, Galois, and Cubic. I should have put Cubic on, so apologies, John. So we have so I think we're really we have an excellent team, and we also work with the kind of best of breed consultancies specialist consultancies in the Haskell ecosystem. It's decentralized, and it becomes more decentralized over time. So in the very beginning, the kind of block production of the system was federated. So there was only a small number of entities which could generate blocks, and then a big step was really decentralizing the block production, and we have these so-called SPOs, which are called stake pool operators, and that's a bit like a miner in the Bitcoin terminology. And these are people who really are running businesses that on top of Cardano, they've built their businesses, and they're all over the world, and there are hundreds and thousands of them who are doing that. So they're the ones who are responsible for block production, because an individual, maybe you don't want to have a computer running all the time. So what you do is you delegate the right to do that to these stake pool operators. They take care of having some infrastructure, and then they distribute the rewards. And this is all happens automatically. You don't have to lock the currency, and it works very well. And then the next step in terms of decentralization is decentralizing the governance, so people can make decisions about how the system is going to develop and that kind of thing. And that's something that's happening right now. So this functionality has been rolled out, and at the moment they're having 50 workshops around the world to get input from the community, and then they will have a ratified constitution soon, and that will progress. So decentralization is a big focus. Right, now on to formal methods and how we use it. So let me just say a little bit about the formal methods team so you get a bit of a picture. And we had a reviewer comment who was wondering about the kind of size of the team. So I thought should mention this. Formal methods team is not enormous in IO. We have 11 specialists. We do have some open positions. And we have a kind of bigger group of people within the company who are interested in formal methods. So, I mean, we have about sort of 20 people who regularly attend our meetings. And of course, we work with other people in the teams as well. So the default model that we try to follow is to have formal methods engineers embedded in the teams. We don't want to be a separate entity doing different things. We want people to be in the team, providing value to the team, and it should be really part of the process. We are kind of spread across the company, not terribly evenly, but yeah. So that's something that I think will increase over time. So we work on the Cardano node, on smart contracts, on Midnight, which is a different project, on JED, which is a stable coin running on Cardano, and in R&D, so bridging the gap between research and development. As we work in those projects, we really have sort of two priorities. One is in R&D, we're really focused on bridging that gap, taking something from research, getting it ready to be implemented. And then on the engineering side, we're kind of, as I said, we're working with the team, and we're trying to provide that extra level of high assurance, and also to accelerate future development, so to put people in a position where their code is trusted and is well understood, and then they can, if they're considering changing something, they can, they know that feel safe about what they, the system they've got. There aren't any kind of hidden gotchas, and they can examine the trade-offs and things. So that's the kind of position we want to put engineering teams in. Oops. So let me say, so I've put this on a red slide, it's green on there, which is confusing, okay. But yeah, a different colored slide. So this is the strategy we adopt. We try to get involved in an early stage, so ideally at the research stage. We develop formal artifacts that can grow and change with the project. So, that means they can't be too heavy, or they shouldn't be too light. So we want things that are adaptable, and we can, as we work with the team, we can kind of tune what we're doing. And we also have to tune the level of formality to the project. Different projects, we can do different things. So some things are easier to apply than others, some things are more important, so we have to be adaptable. And a key thing, this is really the continuous part, is that we want to lock formal methods into the development workflow via continuous integration and testing. So we don't want it to be a separate document in a separate repository that somebody has to change the code and go, oh dear, I haven't updated the specification, and then they drift over time. And this, so by doing that, we keep things in sync, and it also forces us to be able to go as fast as the engineering team, and I think it enforces a lot of good qualities the same way as it does for integration and testing. And another key thing is that we want to be involved at the late stages of development. So we don't want to be like an intervention. We want to be involved at the late stages of development because that shows that the approach is working. But the main thing is, as I said, it puts people in that position where they've got, they know how their code works, and they trust it, and then they can move forward from there. So rather than, let's say, they consider a new thing, then they have to go back to the very beginning and model it from scratch. So that's really the aim. And I think getting to that point where you can make those changes with confidence is really important to the health of a project. So rather than kind of like, you become a victim of your own success and you don't dare change things, I think it's good to be in that position where you can be agile. So I'm going to talk a bit about the Cardano node. It's very confusing, my slides are green because it's all white and red on my screen. Okay, so the Cardano node is the software that runs on the stake pool operators and other users are running on the network, and this is a live system, right? So this is really about changing. It's a bit like changing the tires while the car is driving. So making changes to this and introducing new things. So the high-level architecture of this is that we have we try to, as much as possible, to have a pure core and then sort of isolate the complicated stuff. So in the middle, we have the smart contract layer, and the smart contract approach in Cardano is based on a very simple fundamental. So a smart contract is really like a kind of a decision procedure that can just say whether or not it's a sort of custom decision procedure about whether you can spend some money. So it's like a sort of custom lock. So it's quite a simple model. But when you connect this with tokens, and we have native tokens, then this gives you quite a powerful model. But that's very simple. It's just a decision procedure, just a function that says yes or no. And then the ledger rules are also quite simple. That's just a simple, it's a simple state machine. So the state is the kind of current state of people's wallets, or everybody's wallet, and the current state of the money that's held in the treasury. And then the transaction is the input to that state machine. And then if it's a valid transaction, then you go to a new state. So that's quite a simple concept, and it's amendable to formalization. Consensus is the next layer, so that's sort of not really interested in what's in In the blocks, it's interested in maintaining a block tree of all the different chains, which may include forks that people are communicating. So it's maintaining that tree. It's determining which is the best one, and it has to kind of track that information. And then you have the networking layer, and that's about maintaining connections with the other peers and being asked to send a message, asking for more information. So this means that you can put the I/O and the concurrency stuff into the outside here, and you keep the core simple, as simple as possible. And then you have the node, which kind of ties this all together. So I think a pure core has been a big part of the design approach here, and also this idea of designing for testing and verification, designed to make those things easy. I'll say a little bit more of that in practice about how that's applied to use for testing things like disk I/O and other things. So I think having that going into this process with that in mind has been a big thing. And also, when it comes to verification, having these simplified, this sort of simple core where the ledger, for example, isn't, the code isn't polluted by things to do with consensus or I/O. I think that's very helpful. So let me say a bit about the smart contracts. So the smart contract system, the surface language is called Plutus TX, and it's basically like a subset of Haskell. So people can write their code in Haskell, and it's compiled to a low-level language called Plutus Core, which is not actually that low level. It's actually based on lambda calculus. So it's based on system F omega mu, and in fact, the types are actually erased in the last step. So really what's running on the blockchain is really untyped lambda calculus with some extra primitives for things like cryptography and byte strings and other things. So it's quite a conceptually simple language, and the idea was to keep that as simple as possible and something that's well understood, because backward compatibility with blockchain is a massive thing. You still have to be able to run all the contracts that people wrote in the past. So maintainability is key, and they have this system of having a sort of stable language but the built-ins are things that might change. So you might swap out a hash algorithm, put in a new one or something like that. But the idea is the main language stays the same. We have an AGDA specification for this, which is kind of like a language specification. And this first paper, System F and AGDA, Fun and Profit, is about that. So it's intrinsically typed and scoped, which makes illegal states unrepresentable, which is a term was mentioned earlier today. We have a reference implementation of that evaluator and a reference implementation of the type checker. So this is in AGDA, but you can compile it to Haskell and run it. And in principle, you could just take it and plug it in to the production system, but we use it for testing. And then there's another piece of work. So this is something that has come. So the first paper is something that we kind of developed as a team. The second paper is where IO has funded research at Utrecht, and Jaco, Manuel, and Gabriel and Wouter have worked on translation certification. So this is this grey box idea to compiler verification or certification. So at each stage, the compiler can output the intermediate language that it's working on, and then you can then separately check if it's preserving the meaning of the program. So you get a certificate for a specific program rather than a sort of concert like from scratch certified compiler. And that's something, so that work is something that we recently put into practice. So that's used now on the untyped optimization passes in the production toolchain, because that's somewhere where there's more risk, because having the types earlier on actually catches a lot of problems. So that was a sort of area, right, this is where we need to do some extra stuff. And as I said, this reference implementation is used for conformance testing, so we can generate an arbitrary Plutus contract, and we can run it on the production evaluator or the reference one, and we can see if they give the same answer. Yes, this AGDA-generated certification code is actually in the production tooling. I would like to get, in the future, to the point where we have verified code in the node, but this is an important step where we have it in the tooling. Here's a little example so this is the this is the evaluator. This is the CEK machine. It's a bit of the CEK machine. So this is intrinsically typed, takes something in a state T, a state of type T to a state of type T. So if it's a variable, you look it up. If it's a lambda, then it's already a value, and you change modes. If it's an application, you stash the argument and you carry on processing the function. If it's a type function, it's a value, so you change modes. If it's a type application, you stash the type argument and keep processing the function. And so these are for the recursive type, so you kind of go inside these things. If it's a constant, then that's a value, change modes. And this is the rule for if it's a built-in, an unapplied built-in function, so we just consider that a value. There's some more complicated things you need to do when you actually apply a built-in function. And then we have an error code which stops evaluation. And this is, so that would be something like divide by 0, or where you verify signature and it doesn't verify, that kind of thing. So that's intrinsically typed. Okay, so let me say a bit about so that was sort of the first case study. Let me say a bit about the ledger. So the ledger has gone through various iterations. So the system has gone through various iterations, and the ledger has evolved at that time. So the Byron system is this federated system, and they had a big separation of the spec and the implementation. So the spec was kind of retrospective as a way of understanding the code, but it was written in LaTeX and mathematical notation, so that really gave a good understanding of the problem, but it wasn't very well connected with the code, and people were not terribly happy with the code at that time. So then they tried something new for the next step. So in the Shelley era, this is when they made the system decentralized, and they had these stateful operators. Then they had an upfront specification in LaTeX. They wrote a reference implementation, which became a victim of its own success and became the production implementation, which you can think of as a good thing or a bad thing. So they kind of had a rewrite of the system. There's still a problem, though, in that this gap develops because they were under pressure. I mean, that's the engineers are always under pressure, and then the specification and the code diverge. You implement optimizations in the real implementation, and then it's harder to see if this matches up. And at the same time, they also wanted to do better with the testing. So they used to generate whole kind of blockchains to test, but people still worry about, I think there was another nice comment about, being paranoid is a good plan. So I think it was put rather better on the slide, but anyway. So it's good to be paranoid. So they were worried about the coverage of their testing approach, so they wanted to do better. In the Alonso era, that's where they introduced smart contracts. So here we had the extended UTXO model. So that was a kind of separate research effort to kind of develop the functionality in a simplified way, with a kind of paper and a prototype and a formalization, and then that was then applied later. So that was really where we kind of, that was a piece of research which fed in. And then in Conway, so that's the new era where they have governance, then they've evolved the approach. So now, to avoid having this gap, they have an AGDA specification instead of a LaTeX one. So that can generate a PDF that people can read, and it can also generate Haskell code, which you can use for testing. And they have a new approach to testing, and this is something where they work very closely with Cubic, and it's about generating states. So not generating whole chains, so they can generate states, and then they can explore particular interesting areas, and also do more advanced testing where they can mix randomized testing with certain places that they want to get to. So I think people are much happier with the testing, and that's been a big advance, and also closing that gap. So as I said, that's used for conformance testing. We also have a paper which talks about this AGDA approach to the ledger specification, which was at FMBC, I think. And this UTXO paper was, I can't remember where it was now. Okay. Here's a bit of a flavor of a rule from the ledger. Rather annoyingly, this rule is actually about checking the script, but this seems to be where the state gets updated. So the system is a kind of hierarchical state machine,
where there's a different state machine for checking different things, and it all fits together. So there's another rule where it actually checks the things, but this is where the state is updated, and this is what I really wanted. So this stuff along the top is the kind of above the line is checking stuff about that the scripts are valid, but here, you go from a state S via a transaction, and then, a transaction has inputs and outputs. So the inputs are the things you're spending, the outputs are the things that are being produced. So you have to subtract the inputs from the UTXO set, which is the money that hasn't been spent, and then you have to add on these new outputs, which is the new things that can be spent. So that's that update. And then a transaction, you have to pay some fees, which goes into a central pot, so that has to be updated. And there's also some deposits you have to make to stop people making lots of tiny transactions to slow things down. And also you can donate to the treasury if you want, so that capability is there as well. But that gives you an idea, and this is very similar to how you would write it in LaTeX, but this can be turned into a function that can be run. And we have a tactic that turns functional relations into functions that we use. So that gives us a kind of nice middle ground. In consensus, so this is a more challenging area. So they've used the type system to enforce things, and Simon Peyton-Jones said at ICFP the other day that I think that the type system is the most, is the most well-used formal method. So this is where they've really tried to use the type system as much as they can. And they've also gone through a process as the algorithm has been developed. So these are based on peer-reviewed papers written by our research department, and this team has also evolved their testing approach. So they used to test by simulating a whole network of interacting nodes, and now they prefer to test having a single node and then within an environment. So the environment would represent how it's talking to the network, and they find that more effective. And at the same time, we've also recently introduced an AGDA specification, and we did this by going to talk to the team and saying, what are your biggest concerns? How can we help? And they said, well, the block header processing, which is quite a simple thing. So is something that we would really like to have a formal spec for. So that was the first thing that we did. So yes, so that's kind of like it's a bit. So the blocks are split into the bodies, which the ledger people care about, and the headers, which the consensus people care about. And this was a place they were keen to have something. So that's what we've started with there. And this is a rule. I'm not going to go into details, but it's you can see it's similar in style to the ledger rule. It uses the same framework, which we can reuse. And here, you have a state, which is some certificates and some nonces, some random numbers, and a pointer to an earlier block. And then when you process a new block header, if it's okay, then you update all these things. So it's the same kind of approach. In networking, they also have used the type system extensively. They have kind of mini protocols, and then they encode these in the type system, so the code can't do things that are not allowed by the protocol. We've done a lot of performance modeling, particularly of block diffusion, which I think I have on my next slide. So to think about how long it takes for the whole network to get a block. The networking layer is very reliable. We have very good uptime with our system. And it runs on the public internet by individuals, so it's a decentralized distributed system. So this is a big success. And this area also uses kind of mock testing, so they can simulate disk access or disk errors and concurrency and cryptography by using IOSIM. And that means they can actually, the production code is parameterized over these kinds of activities, as I said, concurrency and disk access. So they can kind of they can test and use in production the same code. So that's very nice. And this is a paper which is about the performance modeling. And here's an example of this. So that what we want to achieve is that all of the nodes in the network get the next block in 5 seconds with 95% probability. And then you can think about, well, how big can we make the blocks? Or if we wanted the block to be a certain size, how fast does the network want to be? We want the network to be all over the world, right? So you can, my point is, here it is. So if you sort of read up from 5 seconds, you can see that A lot of these things are too big, so we're kind of in that region of 64K, 256K are okay, but the other things are too big. Right, so that was the Cardano node. So let me say a bit more about, R&D. So this is kind of a different emphasis. So this is about research driving engineering. So what we want that to be a smooth, effective process. So I really like this definition of innovation. So invention is a flower and innovation is a weed. Right, so it's really about adoption. It doesn't matter if you have the world's best idea, if it's not just going to kind of grow on its own. So, and this is from Robert Metcalfe, who I think he invented Ethernet at Xerox PARC, and but to get adoption, he founded his own company, and he put a huge effort into into sales, into talking to customers, finding out their problems, and I think that's the thing. It's not just, the idea, he already had the idea, but it was really that effort and focus on innovation that made it a success. Going back to our innovation process, so in R&D, we're focused on taking these, well-chosen ideas from research, and we follow a software readiness level system, which is a bit like NASA's TRL system. So a research idea is kind of SRL1, and a system in production is SRL9. So we're trying to get things from 1 to sort of about 6, say. So that's kind of like within a 4, 5, and 6 are kind of like, you've really explored the area well, you know all the trade-offs and things, but it's in a kind of laboratory environment. So you might think with something that's got to work in space, at some point you might be just kind of testing it underwater. So that would be a realistic level. So that would be somewhere in 5 or 6, I think. And the idea is we want to take these ideas from research, and then we want to get them to a point where they can be implemented by a production team, even outsourced. So we would like to get to the point where we know exactly what we want, and we have the mechanisms to be able to judge if something is built externally, whether it meets the specification. So we want to go through that process in about 6 to 12 months. We have an interdisciplinary team. We have all the relevant people working together. So we have the kind of basic templates. We have a researcher, a full methods engineer, sometimes a cryptographic engineer if it's relevant, a product expert, an architect, and a prototyping engineer. Changes a bit. Sometimes we don't have one of the roles. Sometimes we double up. We tend to have researchers and product experts split between multiple projects, but that's the kind of basic template. And we also work with with the research team on the other side, and with the engineering team on the other side, and with the community. So we want to, we want to do that communication as well. So here's a couple of examples. So I have 2 examples of R&D projects. So this is Ouroboros Peras. This is the next iteration of the consensus algorithm, which is aimed at fast settlement. So this is about speeding up the settlement, which is probabilistic, and it's kind of the way I imagine the UI is a bit like when I make a bank transfer and it says, well, this might take 2 hours, or it might take 1 day, and then 5 minutes later it says, oh, your money has already been sent. So this kind of gives you that earlier settlement, which is very valuable. This is one of 4 consensus projects that we are currently working on. We're working closely with the researchers, so we have a sort of good feedback loop with the researchers. The innovation team has given feedback to the researchers, which has changed their design, and the paper is something that they're planning to submit soon. We have a relational form model, and this is sort of based on approaches that are similar to some work by Baz Spitters and Ilya Sergey on how to formalize safety and liveness for consensus protocols. We experimented with a monadic DSL for the cryptographic pseudocode, which is how the researchers write their protocols. So we want to also work with the researchers. We'd like to have a common language to do that. So that's something that we've experimented with in this project, and we plan to do more on. We're using QuickCheck Dynamic in Agda, so it's compiled to Haskell with Agda 2HS. So that's a state machine testing approach developed by John Hughes and others at QVIC, and that's about, as I mentioned before, it's about exploring the state space, but where you have key areas that you want to explore. We also have a Haskell prototype, so we can use that, so we can conformance test that and test it generally using QuickCheck. And we've also done this performance modeling because it changes things about the blocks, and also this approach introduces votes, because the way it works is people can vote on blocks, and that's how you get the faster settlement, because you take that into account as well. And we have something called a SIP, which is a bit like an RFC. This is how we work with the community, and this is an example. So this is actually the SIP here. You can see we have, there are 5 authors, which are all in these different categories of, so we have architect, prototyping engineer, researcher, formal methods engineer, and a product person. So we have that, they're all part of that design. This document is actually a literate AGDA file, so it has also bits of the model in there, bits of as the specification. So that's something like an RFC that we want to get discussion, and that's a kind of a document which explains how this has been explored. And this is at sort of SRL 4. And this is the development process model that they follow in which is rather complex. We have some other ones which are simpler, but this is very interesting because it has has 3 areas really. There's the research paper on the left. There's the AGDA specification, where we have the specification and the test model. So we're not sort of doing conformance testing there. It's kind of like there's a soundness argument. And then this is compiled to Haskell, and you can run a Haskell prototype. You can also run things such as a Rust prototype against this system. So this is how they do it. So there you go. And on the research side, they have this pseudocode, and then also we want these safety and liveness theorems. Let me say a little bit about another one, Babel fees. So this is about where you might want to pay for a transaction on a chain A with tokens from a chain B. So you don't, maybe you don't even know you're using blockchain, you don't know what the underlying currency is, you want to pay in some other currency. Then this is a system where you can sort of offer, well, I would like to pay in this currency, and maybe you can be matched with somebody who is willing to pay your fees in ADA, in our case on Cardano, and would take what you're offering in return, or maybe they're presenting a service where they're going to pay all the fees. That's another model. So this is really, so the previous project, the Paris project, is really aimed at changing the consensus protocol. This one is more really a change to the ledger, and we have a formal model for that, which builds on this AGDA model for the ledger. So that's showing that by being involved in at a late stage, we can build on things we've already got. So that's really like a direct PR to the ledger formalization. And we also have a Haskell prototype, which is a PR to the Haskell implementation. And this is so that there was a research paper about this previously by my colleagues, and now we have a SIP that's ready for discussion with the community. So just a little glimpse of that is one of the changes is changing the transaction body to allow also for you to be able to say, well, I'm going to fulfill, I'm going to pay some extra, essentially, I'm going to fulfill some demand, or I might say, well, there's something missing here, I'm requesting that somebody else provide that. So that's this sort of extra change, and this is some Haskell code in this case from the SIP. Okay, so that was kind of the overview, the case studies. So let me say a bit about, so kind of reflect a bit on the approach and also the challenges of applying formal methods. And this has sort of partly come out of a discussion with my co-authors. One of the reasons we're having this discussion, that was one of the reasons we decided to write this paper. And this also reminds me of so there's a very nice experience report in the last session of ICFP by Pedro from Standard Chartered. He sort of called some of these myths. So some of them, it's a problem. It comes down to interpretation, I think, in some ways. So one of the potential challenges with formal methods is how can you integrate it with development practices and also kind of with the tooling. So one of the things, so Arnaud, my colleague, he's a really big fan of kind of pair programming, mob programming. He would sort of like to block off the afternoon in his calendar every day to work with his colleagues on a technical challenge. But that relies on everybody kind of you need to be quite a homogeneous team to do that. And this also sort of ties in with this agile, if you take the kind of textbook agile approach where the idea is that you have all these different tickets or stories, and really anybody in the team can take them on. So But the other side is that you might want to have an interdisciplinary team, or you want to have specialists in different areas. So these things, you have to find a balance there. But there is, inevitably, if you have somebody working in a team who's responsible for one area, you do have, that comes with, that changes the way things work. So that's inevitable. And also the development practices, kind of the tooling, you want to be able to think, I think we have a good argument for that because we have things tied into CI. But yeah, so these do pose challenges. Yep, 5 minutes, okay, I better get a move on. So there is also, it's a specialism for methods in the same way as functional programming is. So, there are fewer people. And it was interesting that Pedro said he actually finds it easier because then it kind of narrows the search, looking for people who have this expertise, and they are better than the average. So I think that's an interesting point. But it is especially when there are fewer people. Also, we tend, particularly in R&D, we're using kind of researchy, prototypey tools. So these are immature. They break. We have to contribute to them. That kind of thing. So we do have those problems, and then this sort of contributes to having specialists and maybe have sort of siloing. So you have to work to make sure these things don't happen. So these are these kinds of the challenges. So I can say how we address those. So one of the things we put a lot of effort into is knowledge sharing. So between the 4 methods engineers working on different things, between we have seminars, and we like to share information, work with other team members on the team. So we don't really have this complete divide. We have people kind of in the middle who can do some things. So that's knowledge sharing. Upskilling. So that's about teaching engineers about 4 methods. So for example, we had an AGDA course taught by Phil Wadler last summer, or was it this? I think it was last summer. And we invited engineers to that. So we trained them in the tools. So engineers, I should say, and researchers. So we trained them in the tools, and they're now on video. So new people who join the company can then watch those lectures. And we've also had I personally, several years ago, I had a similar experience going and learning about Quick Check, which John Hughes taught, which was one of the things, when we were thinking about this AGDA course, was one of the things that I had in mind, because that was where John's company really taught all of the engineers in the company how to do property-based testing, and I think that was fantastic. I think another key thing is having a common language. So I mean that in 2 ways. We actually would like to, when it comes to working with the researchers, I'd like to have a DSL for the pseudocode, but at the same time, the other element of that is also just kind of understanding what everybody else is doing. So we need to learn a bit of research. The researchers need to learn a bit of kind of what happens in R&D. The engineers need to learn about R&D and research. So, we need to kind of expand to get a common language and greater understanding. And we also want to involve researchers at an early stage in the development, and also really involve formal methods engineers and prototyping engineers in an earlier stage. So we don't want to have a kind of wait till the researchers are finished, then we do R&D, then it's passed over to the engineers. We want to have a much more integrated approach with fast feedback loops. And also expanding reach into other areas we haven't looked at yet, and improving the tooling. So, that's always a big factor, and I think that's a big cost saving. It's often a kind of hidden cost, is people waiting for CI or having issues with tooling. Have I used all my time? Oh dear. So I think we've also refined the approach that we use, the strategy. So we try to get involved in an early stage, but we want some level of stability. We would like to have a kind of draft research paper. We don't want something that's changing all the time, or we don't want to do loads of proofs about something that's constantly changing. So we have to kind of wait a little bit and judge, how big a start to make at what point. We want to develop formal artifacts that grow and change. One thing that works quite well is having a small, simplified end-to-end example, which we then add detail to later. So that works quite well, rather than kind of looking at a small area. We have to tune the level of formality to the project, and partly that's sort of knowing when to add detail or add proofs, for example. But also we have this balance between standardized tooling or customizing things to the project. So you have to find the balance there. We want to lock formal methods in. That's really important. But an early, very useful thing is just having a type check spec. So that's really useful. And as I said, we want to stay involved to the late stage. I'm not refining that. I think that's important. And there we go, I'm on my last slide. So we are hiring. We have 3 open positions. We're looking for interns. And I also wanted to advertise some other work, which is about consensus algorithms, which is outside of Cardano. Thank you.
All right, so while you guys set up, we can maybe do 1 or 2 questions. You go ahead.
Hello, hi, really nice talk. So I have one question. In one of the slides, you mentioned that you extract out the ACDA specification to a PDF.
Pardon? Sorry?
Sorry, in one of the slides, you mentioned that you extract out the ACDA specifications to a PDF.
Yes.
So is that in a natural language style or is it still in the...
It's in a kind of mathematical notation. So
okay.
We started off having kind of LaTeX, set theory mathematical notation, and we want to kind of stick to that. So
okay.
We used to write that manually, now we have kind of ACDA that generates something as close as possible.
Okay, so it's not exactly in the ACDA style, but it's more understandable because it's mathematical.
So it's mathematical. So
okay.
It's really cool to our researchers and engineers who are happy with that kind of.
Okay, that's pretty cool. Yep, thank you. Yeah.
So, as we segue, thank you again, James. And, well, something dear to my heart, continuations. Done lots of stuff for me, but we'll hear what they've done for you.
Great. Yeah, so thank you very much. It's a pleasure to be here and present our paper, which is joint with Bogdan. He's the main developer on this project. I'm the main economist on this project because, of course, every project needs an economist. Don't worry, though, it's not contagious, so you should all be fine. So what this is about is continuations and our use of it. Our use of it in what? Well, we've been developing for a couple of years now ConGame, which is a platform for economics experiments. And just to give you an idea of what that is, so I'm going to show you a Hello World example just to fix ideas so that you don't think of experiments in the lab or anything like that. But the way you should think about economics experiments is surveys on steroids. So I'm just going to walk you through a very small one, just to highlight the features that the platform should make easy and what it ought to be doing. So here's a very short survey. I'm just going to type in my name, my favorite programming language. In case you're wondering what it's written in, it's in Racket, and that's my favorite one. So have you ever used continuations in an application outside of computer science? I'm not sure how many of you have done it. So we have, and you'll see it today. But my guess is most of you know, unless you're a compiler, implementer, probably. How many of you know the difference between regular and delimited continuations? All right, so I'm also going to tag yes. I wouldn't want to talk with both of you formally about this, though, but I kind of understand what it is. All right, so now the main thing I want to point out, just going to the next page, nothing earth-shattering at all, but obviously this page responds to what I've done. Let me make it bigger. So, you know, it has tracked my name. It has responded to the fact that I said Racket. It says its favorite programming language is Racket 2. So, in short, this is just very stateful applications is what we want to write on the web. That's the main thing that I would like you to take away, technically speaking, for economics experiments. And finally, just to give you an example, you know, there's going to be a lot of randomizing in economics experiments. Usually people get lotteries, they play games in the game theory sense with each other. And so here in the background, we tossed a coin. I'm going to have to guess. I'm going to guess heads. I always guess heads. Okay, and this time I won. Okay. All right, so this is essentially, it's a web interaction, but the main feature I want you to take away from this is that it's a very stateful web application. It's not just one page and another page. These things can go on for like 30 minutes. We might want to repeat them, and so on. All right, and so this is what ConGame is supposed to and is helping with. But moreover, this was the Hello World example. What really the goal is of ConGame is, because this could be done in anything, is to expand the range of the possible experiments. And what I have in mind here is to a large number of interacting participants, playing market games, essentially simulating market games by having many people interact, over long periods of time, repeatedly, every week, with many overlapping treatments. Treatment means essentially A/B test. It's kind of, I guess, what, you know, in computer science, it's the closest that you get to that. You can also think of treatments in medical experiments, except that economists don't do medical treatments. It might be personalized to each participant. and I might want to track multidimensional outcomes. The important thing about this is that what this requires and why we started with this is because it requires strong composability and reusability features. Because I cannot build this up if every time I do this, I have to rebuild everything from scratch and copy-paste it, let's say. All right, so why custom platform? The example that I showed you might have made you think that obviously this is doable elsewhere. My claim from having used existing tools before is that most of them have very low composability and reusability. And essentially that comes down, it's not quite just that, but due to no or poor notion of what a study is, what therefore the fundamental building block is that we want to compose and reuse. So for instance, take web frameworks, Django, PHP, React, whatever your favorite framework would be. First, there's no notion of a study. So if I want to write it, I have to create this myself. This is going to be used by social scientists and economists. There's no, we don't like coding for coding's sake. This is not something we find fun. And all of these web frameworks expose a lot of web. Requests, responses, database. I have to understand and think about all of these. I don't want to do that. I don't care one bit about it. When I talk to a colleague of mine about an experiment, I don't say, and then we store this on the database, and then I have to think about transactions because otherwise we might overwrite it. That's not how we talk. We just say what we want to happen. Qualtrics, some of you might have seen Qualtrics. The main problem is, and the benefit, is that it's a clicky GUI interface. It's extremely user-friendly for small and simple studies, and it's extremely tedious if you want to do something larger scale. It's essentially not, like most of these tools, no coding tools, composability and building up on each other is very, very hard. Again, therefore, it's going to be fantastic for small experiments and horrible for larger ones. Finally, O-Tree, which none of you will have heard of, but that's like the main inspiration for Congame and the one that I used before. It was built on Django, so a Python web framework. But again, the main problem there is that its notion of study is very bad, and I'll show you explicitly for O-Tree the shortcomings in a little bit. Oh, by the way, I should have mentioned, which I am now, I haven't talked about continuations yet. So the first half of the talk I'm going to talk about what the software is trying to achieve, why we want to do something, and therefore how continuations gave us some benefits, but I'm not going to explain continuations. And then Bogdan takes over and explains specifically how the continuations fit into this and the problems we hit with them. All right, so as I mentioned, Racket is the programming language that we used here, and we are using its continuations quite heavily in the core of Congame. And I hope to be able to convince you of this, but the continuations enable multiple benefits. First, we can use the full power of Racket anywhere. The example will make a little bit clearer what that is, but hopefully it will be. And they allow us also to use a composable study, a notion of a study, what a study is. In particular, it's a recursive data structure consisting of a study, which is a sequence of steps, and each step is either a page or another study. And so, of course, that way it goes down, and you can see how you can then build larger studies from that. And finally, which people who have used continuations on the web may already know, so this is a standard benefit, you can write code in a direct style, which we'll illustrate later on, where I don't have to think about the request and response cycle. I don't have to think about, oh, here I'm sending it, here I'm receiving it, these two pieces need to be hooked together. Now, when I say here, by the way, continuations enable these benefits, I'm not saying they are necessary. I'm saying they provide these benefits. There would be other ways to do it. All right, I don't know how much, you're not going to see very much of this, unfortunately, I think. So probably if people in the back are not going to be able to read this. But let me just say, so this is O-Tree code for the coin tossing example that I gave you. This is heavily edited. It's not the full code that you would need. There would be more. What I would like you to realize is there's one file called settings that has to be changed, one called choices, it's the init really, and one for the results. So there's 3 parts that you need to have. Moreover, since after I flip the coin, which is happening here in the random choice part, and I check whether the player chose the right thing, I have to store this in a global variable called player.participant.ok, which I have to essentially initiate. It's not quite an initiation, but in the settings file. In the settings file, I have to say
please make a field in the database called OK, which can be called via this mechanism. Why? This is so that these different apps, which is how O-tree thinks about studies, so that they can share this variable and therefore pass on the data from one to another. And if you can't share the data, well, then you can't compare, then you cannot make later stages depend on what I did before. Then I wouldn't be able to do that. So you already see here some bad features of it, which did get on my nerves when I was using O-tree, especially having a background in functional programming. First, the code is very non-local. You have to split it up across many files in a way that is kind of unnatural, in the sense of unnatural from the point of view of a study creator who thinks of it as, this is actually local information, I would like to deal with it here, but the software forces you to split it up. Secondly, I talked about the data, the global variables, when you want to share them. You essentially pollute always the global namespace. There's no way of not making it global once the variable has to be shared between apps. And of course, that leads to a lot of problems in reusability, because if there's two apps that call a variable OK to talk to each other, then you're going to overwrite that variable for one, while the other one is unaware that you overwrote it. Right? So this is a standard problem with global namespaces. Finally, something that's not like obvious from the example I showed you, but if I wanted to have two coin tosses, but in different places, and I wanted to reuse that same app, the way I reuse it is as follows. Take the app, copy-paste it, move it over, rename it choices 2, do some changes to it, now you can use it again. This is like the world's most horrible way of reusing. This is literally why I left O-tree, because I had an app called Tasks 5, Tasks 10, and Task Random, which were essentially for running 5 tasks, 10 tasks, or random number in different places in my experiment. And you can see how that's not a composable way at all for doing it. All right, how would this code then look in ConGame? This is the full one hash lang line, for the record is, missing for the study in ConGame. And this is all in one file. What we do in order to share the variables is we define def var at the top, not the usual define. Def var is a variable that gets stored and persisted to the database, which is why you see these set bangs here. The set bang is literally store this variable on the database, which is what it's doing here. So now I don't have to think about the database. I don't have to do a whole lot of things. Moreover, these variables are local to this file. I can export this study in some other file and reuse it without worrying that someone else has called a variable toss or guess. They're not going to interfere with each other. And then if I now wanted to repeat these studies twice, so I defined down here, I don't know if you can read it, def study coin toss. I can now repeat this study by simply saying coin toss 1 is the first step. Well, what do I do for the first step? Well, I run the study coin toss. And then I want to run coin toss 2, which is what? Again, coin toss. These two studies will run. That's all I had to do. No copy pasting and so on and so forth. There's other ways you could do the same thing. Obviously, this dumb code, because you literally just want to repeat it twice. There's other ways of repeating literally the same thing twice. It's just to highlight that this is very straightforward to reuse. All right, so let me compare then just what the benefit is of ConGame here and where I think it comes from. So I think fundamentally the difference in O-tree and ConGame comes from the fact that we have a better notion of what a study is, and we use the better data structure. Secondly, I could use the full power of Racket anywhere. What I mean by this is, going back to the example, I can everywhere before which I should have said, so def step does a bunch of computations first, and then MD stands for Markdown. This is the Markdown page that will be shown. So that means that in this form, I can generate dynamically. I can use Racket to create some part there or to compute it. I can do computations before, and so on and so forth. I don't have to think about where am I? Do I have the full power of Racket available to me? If we go to the O-tree example, I cannot use Python code to generate a page. This down here is template code. It is, what's it called? Ginger, I think. So you have some of Python, but not all of Python. Up here, yes, you have Python code in some sense fully, But you cannot really create a study and pass it around. A study is not even an object that can be created. It's literally configured across multiple files. And so these two benefits of having the full power of Racket everywhere and having an arbitrary data structure based on what we find useful, they are immediately allowed by continuations because they can close over arbitrary Racket code. So we never had to think about it, never had to worry about it. Now you might say, okay, but I could have gotten that without continuations. True, but continuations enabled it without us even having to think about that. So that's really the big feature. All right, so these are the benefits that we got from it, and this is why we were building it and what we tried to get. And with that, I'm handing over to Bogdan to talk about how this all works.
Okay, so like Mark said, we've talked about the why, and I'm going to talk a little bit about how this stuff works. And to begin with, I'm going to start with what, sort of how you might use continuations on the web in the first place. And to do that, I'm going to start with an example to try and illustrate. I'm sorry, this is going to be quite code heavy going forward, so I hope I don't bore you all too much. But basically, this is some piece of code that implements a number guessing game using regular web programming techniques. And so how we normally do that is we have two separate pages, one for picking the target number and showing a form to the user. And so it does just that. It picks a random number, it stores the number in the user session, and renders a form that lets them make a guess and points at the other page, which is where we then, once they submit the form, we look up the number off their session. We do a little bit of validation because now this is a named page, so they might have landed here in some other fashion. Then we take out the guess from their form, and then we compute a response, or we compute what we think their guess was. Instead of this, in a language with continuations, what we can write is something more like this, where we have one page. As before, we pick a random number between 1 and 100, and then we do something interesting, which is we capture a continuation and map it to a URL, respond with the form, and suspend our request handler. So we send the user a form that contains a URL that, when visited, will resume from the continuation of the send suspend call and return a new request representing the user's form submission. Okay, and then as before, we take the guess out of the request and we compute the result. And so the thing to note about this is, one, we no longer need the sort of side channel where to store that target number, right? We simply use, as Mark said, the full power of Racket. We just use lexical scope. We are effectively in the same function. We have a reference to n, and so we just use it. And then also, I would argue that the control flow itself is simplified, right? We just come into the page, we send a response back, we wait for them to come back to us, and then we continue and do our thing. Does that kind of make sense to everybody? Great.
This is what I mentioned, what I meant when I said direct style. So this is what that looked like.
Okay. And then with that in mind, let's think about how we might implement a mini version of Congame. And so to reiterate, the core of Congame is studies that are represented as trees of steps, which are simply functions that generate HTML, and other sub-studies. And then on top of that, we have a servlet that traverses a study object, and this is what we implement using continuations. And additionally, we have these things that we call widgets, and they are what let a participant interact with the study. And you'll see what I mean in a second. And this is a full implementation. This is everything you need in a language that gives you continuations to implement this mini version of Congame. And so what we have here is a struct for steps, which contain one field, the handler. The handler is just a procedure that generates some HTML. Then we have the study, which has one field, list of steps or other studies. And we have our procedure for running a study, takes a study, and then iterates through all the steps in sequence. Its base case returns continue because these calls to run study can be nested within each other. And then if there is a step to run, it calls run step with that step. Run step checks if the step is itself a study, and then just trampolines back to the top to run study. And if it is an actual step, we use this send suspend dispatch function, which gives us a function that will, when called, when applied, will map our continuation, the continuation of send suspend dispatch to a URL. And so we simply call the step handler to produce the HTML and suspend at this point. And then widgets look a bit like this. We could have a button widget or a form widget. A button just generates an anchor with a label and a target URL that uses that embed function that we got from send suspend dispatch to map this function to a URL. And then when this function returns continue, we end up returning continue from to the continuation of the send suspend dispatch call. We end up returning from run step, and then we end up matching on the value. In this case, it's going to be continue, so we're just going to move on to the next step, right? And so this looks no different than any sort of tree traversal code that you might write. And then putting it all together, you might have, you know, a little study that doesn't do much, but it renders, you know, a page with a paragraph that says welcome to the study, uses a button widget to let the user continue on to the next step. And then the next step, in this case, is just done, and it says thank you for participating. And then we put these together inside a study and use our run study function inside a web request handler to actually run it, for a participant to actually go through the study. And yeah, I say this is a mini con game, but really our full implementation, it just has more features, but fundamentally it works the same way. And so next I'm going to talk a little bit about some of the challenges we encountered in using continuations to build our system. And one of them was using dynamic variables with continuation. So dynamically scoped variables, I should say. So Racket has support for dynamic variables via its parameters functionality. And parameters are thread-specific and continuation-specific values. New threads inherit the parameterizations of their parent threads, and in Congame, where we use them is to store the participant's current position within a study. And so Mark spoke about how we store data in the database. And so we use this position to determine where exactly the data should be put in the database. And just a little bit more about how parameters work for those who don't know. Parameters are created using make parameters. So here I'm defining a parameter called current directory, whose initial value is false. They can be changed using the parameterized form. So here I'm using parameterized to change the value of current directory to /home/Bogdan for the dynamic extent of its body. And so when I call display line current directory, it will print /home/Bogdan. Or they can be changed using direct assignment. And so if you call a parameter procedure with one argument, that changes the value of the parameter. But direct assignment mutates only thread local state without affecting any surrounding parameterizations. And this becomes relevant in our next example, where we define a current position parameter whose initial value is null. We parameterize the current position to root to the list root study-1, launch a new thread, display the current position, then directly assign a new position, and then display that. And then separately, we have another thread that just displays the current position. And when we run this code, what we get is some ordering of these outputs, where thread 1 always prints list root study-1, followed by list root study-1, study-2, and then the second thread always prints the empty list because it's unaffected by either the parameterization or by the direct assignment that I've done here. And that when you combine threads, parameters, and continuations, and I'm sorry about this example, it's as minimal as it gets, but it's extracted from our system. You can have this kind of parameter loss issue, where here I have a parameter, p, whose initial value is false. I launch a thread, install a continuation prompt, then parameterize p to p1, then inside the parameterization, install p2 as the value of p, and then capture the continuation up to that prompt. Okay, and I send that continuation over to this other thread, which restores it, and then within that continuation prints the value of p. And so what you might expect, just looking at this code, is for the output to be p2, but actually it's p1, and it's because of what I just said. It's when this direct assignment happens, it's only modifying some state that's local to this thread. So even though it's something that happens within the dynamic extent of this continuation capture, it's not something that survives sort of the capture. Okay, and this was an issue for us because we were trying initially to track the position using direct assignment. Obviously that didn't work, and this was the cause. And the second issue that can happen when you combine all of these things is kind of the reverse of this problem. So here I have an example where I have two parameters, a and b. They both have an initial value of false. And when I parameterize a to the symbol a, install a prompt, capture the continuation up to that prompt immediately, and then restore it and print the values of a and b, I get what I expect, which is just the initial values, right? So f and false and false, because I only captured the continuation up to this prompt, so I expect it to be unaffected by the parameterization. However, if I very slightly modify this code to add a second parameterization within the captured sort of chunk of frames, then what happens is quite surprising, and the output is a and b. And so you can have this kind of parameter revival issue, at least with Racket's implementation of parameters and of these features. And this happens because for performance reasons, the parameterized form ends up extending the previous parameterization that is visible to it. And I don't remember the full details, but it mostly has to do with making the frames smaller and lookups faster. Okay, and with that, I would like to reflect a little bit on our use of continuations to build this system. And I think the main benefit has been that continuations let us implement our study harness, like the core of our system, as just a straightforward depth-first traversal tree, which we probably would not have been able to do, or I know we couldn't have done it with just regular web programming techniques or with like a weaker form of continuations on the web that you see in some languages where you map a closure to random URLs, because that would not have given us the control flow benefits. It may be possible to implement a system like ours using a slightly less powerful language feature such as coroutines. If you don't need the ability for the user to use the back button and take a separate path through a study, which for Congame we don't want, then coroutines might be enough to get sort of similar benefits. But if that is a desirable property, then you would, I think, need multi-shot continuations. The issues we encountered in building the system were mostly due to these surprising interactions between parameters and continuations. If we were to do it again, we would probably just avoid using parameters and pass like a context object between steps of a study and just avoid this problem altogether. Or, I mean, at this point, we know what the paper cuts are, and so, you know, we know how to avoid them, but yes. And finally, I would say also the mental, continuations can have extra mental overhead when you're programming with them, or at least when we program with them, because we don't use them very often. And debugging issues with continuations tends to be quite hairy, and so it would be nice if languages gave us more tools in order to be able to inspect continuations at runtime. So I'm thinking about source locations or which objects are keeping references to these continuations when debugging memory issues and so on. Mark, if you want to add anything.
Yeah, and so just one thing to finish off that I feel after all those years working on it quite strongly is a lot of discussions in computer science often read like, oh, but I could have done this with X, or I could, and the extreme version of that is you could have written this in Fortran, which is true because the principle is powerful. But as an economist, to me, it's like, okay, but what's the cost? Like, what's really the cost? And I think the one thing that I would also take away from this is like continuations were fundamentally the right tool for what we were doing, because what's going on is that what you try to do is you get to a certain point in your code, and you know that if you now got an answer, then you would continue with this thing. The problem is you have to actually send this for someone else to compute. Here it's a participant, it's a human on the other side. Then you have to wait, and then you continue. But that's literally what continuations are made for. So whatever you would try and do, you would be kind of re-implementing a worse version of continuations most of the time. And the part that is so powerful about continuations here is that, again, after you continue, you just literally lose the full power of your whole programming language. The programming language takes care of that you don't have to think about, oh, now I'm in this mode, I have to be careful about which features I use. So it's like, my view is that continuations really made it very easy for us to do this. On the downside, the costs were all these bad interactions with parameters, which were difficult, and Bogdan mentioned the mental overhead. We have this one, I think this is like literally the worst bug, I mean, worst in terms of characters per hour spent. We spent probably as many hours as we had characters at the end to solve it, because all we had to do is, I think, add /delimited, or I can't remember which one is like, what it is like, delimited continuations. I can't remember.
We were using composable continuations when we only needed delimited.
Yeah, so we had to delete the composable, and after 5 hours of running around and trying to figure out where the bug came, well, is this what's going on? Deleted the composable, ran it again, bug was gone. Back then we didn't quite understand what, I think like Bogdan kind of understood, I definitely didn't understand what was going on. Nowadays I'm at the stage where I was back then, he understands what's going on. But the point is continuations are quite hairy in a way that other things aren't. And so that's definitely a downside to keep in mind. Notice, however, that the continuations are entirely hidden from the users. So that once the core is done, again, you don't have to think about it. It's really not something that's passed on to the user. So just the final thing, I think where this, therefore, if you have in a situation, I think the part where continuations can be useful is whenever you have some process where you want to delegate out some work to another process that fundamentally you are not right now coding. It could be a machine, it could be a participant, a human, it doesn't matter. You want to shout it out to some, AI model that you trained or whatever, and then once it comes back, you continue. If you have that kind of situation, I think continuations are fundamentally the right tool to use. The right kind of continuation, so you might have to play around with that, to use, because it is literally the abstraction that you want.
Thank you very much.
So when you capture a continuation and you're sticking it in you stuck it in a URL occasionally, is that right?
Yeah.
There's a problem that occurs there, which is you can end up with a very big URL if you have a very big continuation. Were you just careful to make sure that you didn't have large continuations?
No. So we don't stick the full continuation. We don't serialize the continuation.
Oh, you're not serializing it?
No. We just keep it in a hash. This is what the website does for us. We keep it in a hash. We generate a URL, and then
Oh, yeah.
URL, and they come back to us, and then we resume from the hash.
Oh, okay.
That's also why the full power, you don't have to think about it.
Right. So we can close over things such as a database handle, and it will continue
Yeah, no. Okay, that version makes sense. I have a different question. Do you know what effect handlers are?
Vaguely, yes.
They're the right way to program with continuations.
I know.
They give you a bit more structure. You get exactly the same. You won't get any different expressive power, but it's a bit easier to isolate what the hell's going on.
You get more expressive power with continuations, right? Because you can use
No, you
continuations
couldn't. They're equally expressive. But I'm not sure what current support in Racket is like for effect handlers. We built a library to do it a number of years ago, but it wasn't used in anger. But it might be an interesting follow-up. Absolutely, yeah. I mean, there are languages like OCaml only have single shot, but it basically lets you do the same kind of things, but you isolate the weird control functionality behind an interface so that it's all contained in one place. And you can also compose different functionalities together. If you're just doing one application, though, maybe you're fine, and particularly if you're in a language like Racket. Yeah.
Anyone else? So if I can follow up to that, so yes, right? But the Racket web framework predates pretty much the popularization of effects and effect handlers. The problem is parameters, right? So if you did those via effects, you would get similar problems. And that's because parameters predate threads, right, in sort of scheme history. And the problems of that have been known for a very long time. So we did, I think we did a paper about 20 years ago. So I'm very gratified to see that in your paper because we kind of argued this on sort of principle, right? That so parameters are this fundamentally unmodular construct that conflates like three things, right? You have like assignment, bad per se, right? You have this sort of dynamic binding thing where you want to associate, really what this is about is associating a bunch of data with a continuation. And then there's this inheritance thing that gets passed from one thread to the next. And then kind of, it used to be like it's essentially just a mutable variable, right, before threads, but then because the introduction of threads, they had to become thread local, which adds another dimension of unmodularity to the whole thing, so we get this current mess. So, but I remember that at the time we were widely, everybody said, well, but it's the practical construct, it's the one that you want, right? And we were like, it's going to cause problems because of the unmodularity, but we never really made the case based on real-world examples, and you did. So that's wonderful.
I like how you said, this was widely known because when we posted this PR question of what's going on Racket, Ryan Telfer came back with it is known. You feel like Game of Thrones. It is known. So,
yeah.
Really, is it? Okay,
yeah.
Fine.
Yeah.
To be fair to Ryan, he said this is known but not widely.
Yeah. Well, it depends on. Widely known within the scheme, so widely known in a very narrow community. So, of course, I don't think parameters in that particular shape exist anywhere else. Would be surprised. All right. Anyone else? Then thank you again. So we enter break and we reconvene at 16:00, 4 o'clock.
Okay, welcome back. The final session of this FUNARCH. I'm going to go and, yeah, thanks. That's lovely. The final session of this FUNARCH is Marcus. You have to admire the combination of the authors' names on this paper. We've got Marcus, Marcus, and Marco, just to be really confusing. One of these authors is going to proselytize to us about bidirectional data transformations.
Thank you. Yeah, so I'm the second Marcus on this paper. So not the one with a C, but one with a K. So that's our little abstract. You don't have to read that. Before I go right into the talk, I want to draw some attention to this website I'm currently working on. So we have the functional architecture workshop, but I'm not sure if we all, any of us agree on what functional software architecture even means. And that's what I try to do with this website. So if you go to functional-architecture.org/wip.html, so it tells you that this is certainly like a big work in progress at the moment. So if you go there, then you see this website. It says at the beginning, like you can go to this GitHub repository to work on that website. And I invite you to contribute to that. So what is it about? It says functional software architecture, functional programming in the large, and then there's this sentence that you probably read somewhere already. That's from Mike. I just took that and put that on this website. And then I talk about some values that we as a small community, but maybe growing community share, and I'm like, that's what I could come up with, and I hope you agree, or maybe if you disagree, you can go to the GitHub and we can have a discussion. It goes on to principles, something like immutability, pure functions, of course. I could come up with a few more. And then, so idea is that these principles are the ways in which we try to work towards these values up top, right? And to be even more concrete, there's a section called Patterns, Tools, and Techniques, where the idea is that we have like a bit of a pattern, a collection of patterns at some later point in time described on this website. So I just wrote down some titles basically, and the text that you see is mostly blind text by now. And one of the patterns here is bidirectional data transformation. So I think that is a pattern, and that now leads me to the actual talk that I'm doing. So for the theoretical foundations of what I'm going to talk about, I'll not go into these too deeply. You can read a paper like the Combinators for Bidirectional Tree Transformations paper, which is quite nice. So motivation, right? You know, like the first sentence on the functional software architecture website is roughly this sentence minus the lenses. So now we want to use lenses in large and long-lived software projects released to real users in industry. So this is an experience report mostly on how we do that at Active Group. And so my focus here is to shine a light on this pattern business. So I think that the bidirectional data transformations pattern, if it is one, has some educational merits in that it showcases some of these principles that you saw on the website quite nicely, such as composition and closure, correctness by construction, everything is a value, purity and immutability, and so on. So the industry that we're talking about, so that the industry that gave rise to this talk is in manufacturing semiconductors, which is a complex process, usually performed in heterogeneous IT infrastructure. And we build one system that has to deal with lots of other systems in the neighborhood. And so there's a lot of data ingress and egress happening there. Yeah, here's a slide on some numbers that I'll not go into much. So that is the project that gave rise to this talk, but I want to discuss the ideas with a much simpler application, which is basically the blueprint of lots of web kind of applications, right? So you have a core domain in the middle. I hope this is large enough now for the people in the back, yeah. You have a core domain, core system in the middle with your domains objects, which are these rectangles, these colored rectangles. And you have some kind of user interface, mostly web user interface these days. Some storage, right, on the bottom. bottom here, and then some other service that you depend on. So to focus on so we have a lot of these double-headed arrows here in this picture. Right? So there's data going away from our system and also going from an external system back to ours, to our core system. And in the traditional architecture community, for the double-headed arrow on the bottom here, going towards the database system, there were solutions. Let me make it a bit smaller. No, doesn't let me. Such as ORMs, right? So in the beginning, somewhat in the beginning, object relational mappers were created. This has made a lot of people very angry and been widely regarded as a bad move by now. So this is actually, like, in the traditional community, regarded as a bad move also, because like these object relational mappers that try to automatically deal with this persistence story for your domain objects, that brings a lot of problems with it, as you can imagine. So even the traditional architecture community has moved away from that. So what they now do is looks more something like this, where they have this custom data access layer, sort of on top of the storage system, you could say. And then they write little transformations back and forth to a representation that is like sort of local to this custom data access layer. And this representation, they usually call data transfer objects nowadays. So if you Google that, you will find like a somewhat different notion, because in the beginning, like this is Patterns of Enterprise Application Architecture is like a patterns book for OO patterns by Martin Fowler. That talks about data transfer objects as well, but the original idea was to package up data that you avoid, like doing lots of round trips. That's no longer the main raison d'etre for the pattern. So nowadays you just say that the data transfer object is a separate representation from your core domain, which caters more towards storage, for example. So it caters to serialization and deserialization. So, but now we see, like, in the beginning we had this double-headed arrow at the top, right, the gray one, and then Hibernate, or like these object relational mappers, they wanted to like get rid of this double-headed arrow for you as an implementer, and said, we deal with that, right, no worries. That was a bad idea. So now the current standard is to have this a bit smaller double-headed arrow that you still have to implement yourself. But so it came back, right? The double-headed arrow came back through the back door, sort of. And yeah, and so if you read on in the literature, I think it's just down here. There's a little quote. Sorry. Yeah, so also from the Patterns of Enterprise Application Architecture, there's this little paragraph that says, don't underestimate the cost of using DTOs. So for example, writing these translations. It's significant and it's painful, perhaps second only to the cost and pain of object relational mapping. Right? So it somehow seems to be that the arrow is still quite large. There's still a lot of busy work that you have to do. And there's a similar story for other interfaces as well. So I try to illustrate this with the boundary towards the persistence layer, but also, for example, for the presentation in like a GUI application. You can find things like the presentation model, which is nowadays sometimes called the view model, I think. You can also find a quote, something like that. Probably the most annoying part of presentation model is the synchronization between presentation model and view. It's simple code to write, but I always like to minimize this kind of boring, repetitive code. So now it doesn't explicitly say that it's like busy or tedious to write, because you have to write like these translation into two directions mostly, but that's what I read into this. And I think, yeah, that's a major part for why that's so boring and tedious. So I want to say like one quick word on the merits of this DTO pattern from the object-oriented community, is that it forces you to decouple, right? It's a way to decouple the two systems that talk with each other by saying, well, they don't talk in terms of domain objects, right? That's a bad idea. They talk in terms of a simpler model that is only like only built for this communication only. So that's good for decoupling. But of course, what happens, since it's a lot of like work to implement these things because of these two-directional arrows that we have, well, these tend to, like, people call they have objects in their system that are called DTO, but these are then passed around throughout the entire system, like over time. So it degrades, right? The original idea was to have this be a very, very local representation, but nobody wants to do the work of translating that back to another representation, so they're just passed around throughout the system, so everything is sort of voided again. So, and I think that bidirectional data transformations, which is a technique from the functional programming community, can help with this problem. And so I have a little illustration of something like that in Clojure. So the project that, as I said, gave rise to this talk is written in Clojure. So I'll show you what that is about. Yeah, so our example will deal with URLs and links and bookmarks. It's also one of the examples in the original Lenses paper. And we use Clojure, and more specifically, we use a library called Active Clojure, which is developed by Active Group. So it's sort of homegrown, but open source. And we have records, for example. So these are modeled after R6 RS records in Scheme, I think. And they look like this, right? If you want to have a notion of a URL, we define a record type for URLs with a constructor, a predicate, and some accessors. You can ignore the first fields over here on the left. The names on the right denote, or they name accessors for the 4 fields that we have. So there's a protocol, host, port, and path to a URL. And then we can call the constructor to construct a value like this, and we can use the predicate to check if a value is of that type. And we can use the accessors as functions to destructure and get back to the original values. Right, so very simple. And now for the data transfer objects, the idea is that they don't, like in the object-oriented community, the idea is that there's like only data, no logic, which is quite convenient for us functional programmers because we do it that way anyways. But it also has to be like serializable, easily serializable. And we, in our case, use EDN for that. So that's a sort of a subset of Clojure, something like JSON. Like JSON is a subset of JavaScript. EDN is a similar subset of Clojure syntax. So there's something like a map here with the curly braces, and then we use keywords, which is this colon stuff, purple, on my screen at least. Yeah. Color has been fixed. So here for this function that maps a URL to the EDN format, takes in a URL and outputs a map that has a field protocol, host, port, and path, and the values are just the corresponding parts of the record, right? So if we call URL to EDN for our URL1, we get this representation down here. So this is what we just wrote. And now, of course, we need, well, of course, maybe of course, but in our case, we need the other way around as well. So maybe we send that over to a database for persistence, and then at a later point, we want to retrieve URLs. So of course, we need EDN to URL also. And we write that simple function to write, right? We get the EDN, which is a map, and we can access the keys with just by using the keys as functions. And then we call our constructor. So that's simple stuff to do. And there are some examples here. But now, as you can see, like this is the boring, repetitive, tedious work that you have to do. If you want to transform your data in 2 directions, you have to write 2 functions, one might think. But of course, these 2 functions that we wrote, they're not just any functions in our code base that just like casually meet somewhere. They are very like coupled to one another, in that they are, in this case, inverses, and they should be inverses in this case. So maybe there's a technique to deal with that in a better way. skip that. Yeah, and so the technique that we use to deal with that in a more composable way is lenses. And conveniently enough, the active closure library also provides a lens namespace, which works like that. So there's a yank function, which takes some data as the URL1 and a lens. And we already saw lenses because the record that we defined, the accessors, you could like use them as accessors, as functions that get you the data, but you can also use them as lenses. So in this case, this just gets the URL path from the URL. And this we saw before, right? So this is sort of just a shorthand for yank operation. But if you want to update some URL that you already have, add a path, right? You can also use the URL path accessor as a lens to shove a new value there. So in this case, you end up with functionalarchitecture.org/overview.html, which is not correct, so I update it. I wanted to call this page overview, and then I realized it's work in progress. So. That's the website you just saw. Yeah, and there's also a shorthand for shoving, which is there's simple like arity overloading in Clojure. So you can call the URL path as a function with 2 arguments, and that is basically doing a shove. So this line right here is a shorthand for this line, you could say. So records in themselves give you lenses, but that's not enough. We also have lens combinators or lens constructors for the usual Clojure data structures, such as a vector, which is literally written like this. You can call lens at index 1, for example, to get a lens that points to this 42 in this case. So if you yank from that, you get the 42. And for maps, which are often used in Clojure, associative maps, you can use lens member with a keyword in this example, and then that points to the 23. And then I wanted to, in the beginning I said that this shines a light on some of the principles of functional software architecture, such as composition, right? So of course I have to talk about combinators for lenses. So here's one, sequential composition, written with this greater than thing. So in this case, this takes 2 lenses to first look at the A part. Now I just showed you that lens member creates a lens pointing at a keyword. You can also use keywords right away as the corresponding lens, also a shorthand. And at that value, I want to look at the 3rd position in this case, so that if I yank with that lens, then I get a 69 here. There's also other combinators that I'll not go into. And then there's also projection. So often we have, the Clojure community likes to use ad hoc modeling with vectors, for example, or these maps that we saw. So if we want to represent a quote, for example, we could use this tuple vector syntax, where there's an author in the 1st position and a text in the 2nd position. Or another representation would be a map with an author key and a text key. Right? And they mean the same thing, they're just different representations, so there should be a bidirectional transformation between the 2, and we can use project, the lens project constructor for that. So that takes a map, but that's just syntax, where you list the output lenses mapping to the input lenses. So here we want to map author to at index 0 and text to at index 1. And so now if we yank from this representation, so the vector representation of a quote, with quote vector to map, we get the map representation. And the other way around you can do with shove. Now here's a bit of a problem because we don't know where to shove into, right? So the Foster paper calls this the missing value. We have to provide this here, just as a dummy thing. And then we can shove with this lens that we defined, and that's the data we want to translate, and that gives us back the vector representation. And then finally, well, not finally, but now we get to inverting projections. So instead of calling shove with this dummy value, we can also invert the quote vector to map lens and then provide the dummy, empty, missing value here. And that gives us a lens where we can yank from this map representation, and it gives us the vector representation, just as we did with shove before. And since we're dealing a lot with these records, we also build a shorthand for record projections. So this is the same definition that you saw before for the URLs, but this line is new. It says projection lens constructor make URL lens. So this gives a name to a nice little utility where you can easily make projection lenses with. So it works like this. Down here we can also define this EDN to URL thing that we saw before as a function. Now we can define it as a lens by calling make URL lens, and then we just, for these fields in turn, we provide the lenses in the corresponding to the input structure. So, and now EDN to URL, before it was a function, now it is a lens, so we can get the inverse direction for free by calling invert, for example, here. So we don't have to write this tedious, repetitive, error-prone code anymore. Right, so that's the basic idea. And to build on that, we go on to define a record for links, which is a link is just some URL with a description. And, well, of course, we also want to have links be transformable into EDN notation. So we also make a projection lens constructor for that and build an EDN to link lens with the help of that. So here we say this description is a string that just maps to the corresponding field in the map, but the URL part, now we have to use lens composition to, well, first of all, get to the URL value in the corresponding map, and then this we defined before, right? So here we can compose, and then we don't have to alter what we wrote before, which can just reuse without loss. Now, there's also a story in dealing with mixed data. So if we have a folder structure which has a name and some bookmarks. Now, what is a bookmark? A bookmark is either a folder or a link. So this is a recursive data structure. And this already tells us, well, we're dealing with mixed data, right? So there has to be something in the lens realm as well for that. And, well, we do that with a bit more involved code. So first of all, we have to forward declare EDN to folder because we'll have to tie the knot here later. And then just to show this once, we could have done this differently, but I wanted to show how, like, the lenses that we use, I said you can use them as functions with either arity1 or arity2. Well, you can also define them that way, right? So this is, oh, this is wrong. This is def. So this, oh, no. No, it's not wrong. So this defines a new lens combinator untagged, which takes a tag and a lens and sort of wraps the given lens with this tag. And you can you define a lens with just a lambda with two arities. So this is arity1, takes an x and then does some things that are not interesting. Or it, like with arity2, it takes an x and a y, and that corresponds to the shoving, like shoving y into x. Right, so here it associates a tag with it, and here it unassociates it. And we have a little helper tagged as, which is just a simple predicate. And then EDN to bookmark uses lens conditional, which is another lens combinator you could say. Takes some clauses, and each clause consists of three parts: a predicate on the input structure, a predicate on the output structure, and a lens. So in this case, we ask if we have a tag, like is it tagged as a link, our map, our EDN structure? That is the predicate for the input structure. Is it a link question mark? So that's our predicate for the link record. And if that's the case, either way, we use this lens, so the untagged link, EDN to link lens. And similarly for folders, right? So, but here we need to use lens defer because EDN to folder is not defined yet. So we forward declare that at the top. And EDN to folder is now just make folder lens, which is again the record projection lens constructor, you could say. the name just maps to the name keyword, and the bookmarks maps to the bookmarks, but then we need to map over those bookmarks. So we use map-L, map-lens, with the EDN2 bookmark defined above. Yeah, so that's the brief introduction and how that works in our closure projects. And now I'll move into the more free-form discussion part of the talk. So I have something prepared for that, but I really would like to invite you to like interrupt me at any time if you think something's wrong or missing. And that part is what makes this a pattern, right? I was talking about patterns a lot. I think last year Will Crichton also talked about, like, had a little discussion for the audience to come up with patterns and what it means to be a pattern and so on. And so I have 2 bullets here, which I hope are large enough, probably not. Which is that I think it splits into 2 parts. Lenses and their combinators can live in libraries. I mean, we saw an instance of that, and there are, of course, lens libraries for Haskell and OCaml and so on as well. But the heuristics of when and where to apply them for these bidirectional data transformations cannot live in libraries, right? You have to bring like an actual human thought into that. And that's, I think, the harder part, right? So you can write the library and verify that it's correct once, but then when to apply it is the real question. And the first part is when to reach for this pattern. Again, a quote by Martin Fowler. He also thinks about this, right? When is the DTO pattern the right thing to do? And he says some stuff, but not really a lot, right? So we cannot really find any insight there, I think. At least I didn't find anything. So we have to think ourselves. And I think the general framework is always this. You have some other system and you have some your system, and there's at least like 2 like data flow going up and down, right? So that's the bare minimum. If you don't have this, then you don't have to think about it, I think, in terms of bidirectional data transformations. But then, so this pattern is applicable, I would say, if the same kind of data or the same shape of data moves up and down in this case. But what does that mean? I could come up with like 3 scenarios. Either the external API, so the API for the other system, explicitly tells you that that is the case. Right, so it might be like an API description of some REST API, where it says, well, the shape you get from this endpoint, you can post to another endpoint. It's definitely the same thing that moves in both directions here. But that's very seldomly the case, at least in my experience, that these guarantees are stated explicitly. But maybe they're stated implicitly, so lots of systems give you places to read from and write to, and they like guarantee that they don't touch what's there. We could call this a payload, right? So in the persistence instance, we could talk to a database and write like a serialized JSON or EDN string to some field in some column, and we can be pretty sure that the shape of data that we put there is the shape that we read at a later point. Well, or you just own the other system, so that makes it easy for you to just enforce this guarantee. Or maybe you don't own it directly, but maybe it's in the same building or same company or something like that. So, but this framework where you have some other system and your system, I mean, I wrote down system, but really there's nothing specific to this having to be like full-blown applications that talk to each other. I think earlier in the day, Mike was telling us something about a monolith, right? So people in the traditional architecture community tend to realize that a monolith doesn't have to be unmodular. So you could easily think about this inside of your application as a communication between modules. And to give you a little taste of what that looks like in our daily work is that we use our own library for user interfaces, for component-based GUIs. And there we realized it took a while, but we realized that the relationship between parent components and child components is often lens-shaped, as in this example. So if we were to write a GUI for our folder link URL business that we saw before, it would probably be structured something like this, where we have a folder component, and that is made up of a component for the folder name, which is just a simple string input, and a component for the folder bookmarks, call it bookmarks component, and that in turn uses bookmark component and so on. So that decomposes further. And now the relationship between, for example, the folder component and the string input is exactly that of a lens, because like the string input has to show the string, so the name of the folder. So that's like a yank. So you have to yank out that string from the folder structure. So folder component manages a folder record, as we saw before. So you have to yank out that folder name to give it to the string input. But then also the user just doesn't just want to look at the folder name. They will also want to manipulate it. So they type something else, and that is like the shove back, like a new string is shoved back into the folder component. Right, so in our GUI applications, they often look like this. So this is real code, where we have a component combinator library, you could say, and one of the combinators for components is focus. So up here, test editor is an item. We call them items, so you can also call them components. And then elements input is one of these simple inputs, right? And the relationship between this test editor and the input is described by this lens. So this is a lens in this case. So that's what focus does, right? And we have another focus down here for some SAP endpoint thing, and another focus for some edit requests component, and I think another one down here. Right. Oh. Wow. No. Okay. Yeah, so I talked about when to reach for this pattern, but this isn't like you could say all the time. But it's also important to talk about when not to reach for this pattern, because, well, one instance where I think you have to be careful is when the structures that move up and the structures that move down, they may be accidentally the same, right? Or you could say momentarily the same, but they are not, their meanings aren't the same, right? So we have to be very careful that there might be a subtle difference in the meanings of these structures. For example, in this booking case, so we have an application where you can book a flight, for example. You might think that, well, or it might be the case that at some point during the life cycle of your application, the data that a user sends to our system might look like this, right? And you call it a booking because it has a booking flight number, flight date, and a seat. So the user requests a booking for a flight this way. And then the system at a later point confirms that booking, and what they send back, or what the system sends back to the user is also shaped this way. So you might say it's also a booking, also contains a flight number, flight date, and a seat. But that is just one snapshot in the evolution of the system, because what's really going on here is that the meanings of the thing that moves from the user to the system is different from the meaning that what the system is sending to the user, because one is like a request to, like a, what did I call it, a booking command, right? So at a later point you might end up with something like this, that the user sends a booking command to the system, and the system sends a booked event maybe to the user. And you might only realize this when they are drifting apart, right? So booking command maybe has not a definitive seat associated with it, but maybe just a preferred seating, window, aisle, or whatever. And then booked event, now that has to talk about a specific seat, like 23F or something. And I think it's like, you have to be very careful not to like cling to this bidirectional data transformation. So if you at one point write a bidirectional data transformation for a booking, you might not see that they're actually not the same, and you might not end up with pulling them apart at a later point in time. Right. But there are maybe other cases where you can fall into pitfalls. So that concludes like the stuff that I have prepared, but I really like to invite you to come up with some scenarios and ask questions.
I'm going to use moderator's privilege to say it's very interesting to hear bidirectional transformations talked about now as something that came out of the functional programming community, because it really didn't. It goes back way, way before that. Yeah, I've got a collection of questions. I'm not quite sure how to ask them. Could you say something about the relationship between the way you think about bidirectional transformations for architecture here and the way that, for example, the object management group's original concept of bidirectional transformations as part to support their model-driven architecture came to be?
I don't know anything about that.
Okay, we should maybe talk about this offline. So, a sort of potted history. You put up the paper that came out of Nate Foster's PhD right at the beginning. So that was sort of the functional programming beginning of lenses. But the interesting thing that was happening at the same time was that the object management group was realizing that it needed bidirectional transformations in an object-oriented concept. And so the bidirectional transformation community came out of the conjunction of those two things, both happening in about 2006, 2007. And it's very interesting to see, because in between there's been all this sort of functional programming work which has not been very architectural, which has been focused on the combinators and the small-scale programming. So I end up feeling very old and feeling as though things have now gone full circle, because now here you are talking about lenses for architecture again, which in my conception of history is where it came from in the first place.
But is it like in industry? Is it like used in the object-oriented community? At least what I see, it's not.
No. So that's the interesting thing. So the OMG effort got mired in a whole bunch of problems that the functional programming community is very good at solving, at precise semantics and understanding exactly what these things should mean. But there's lots more to be done to tie these things up, I think. So yeah, good stuff. Let's do lots more. But there is a lot of history that you might find really interesting to look at, and a lot of other papers out of that world. Maybe I could advertise the BX community wiki, which is not terribly active these days but still exists. bx-community.wikidot.com.
Should I open that?
I did check that it was still up.
BX Wiki?
No, BX-community.
Community.
.wikidot. No, wikidot, all one word.
Oh, wikidot.
.com. Yeah. There you go.
I see.
The BX Wiki. So that's one place to start.
Yeah, I saw that there was a Dagstuhl where you were happening in 26 or.
Yeah, that's right. Yeah.
Around that time. So that was already bringing together these communities, or was that?
Yeah.
Okay.
So lots of interesting stuff going on. So what would anybody else?
Could you maybe contrast? I mean, were there notable differences between the way that the model-driven architecture community approached this?
Absolutely, very different. So one thing I'm going to end up kind of improvising my own talk kind of thing, but one thing I'd like to make the case for actually is you said reach for lenses where the same data goes up and down. The way I think about it would much more be reach for lenses when there are two things that need to be kept consistent, for some notion of consistency. Because that's a bit more general. Because sometimes the data, so you can always cast it as the same as some notion of the same data or parts of the same data going up and down. But sometimes it can be quite heavily disguised if you're picking out bits of data from one place and bits from the other, and the formats are quite different. It might not look like the same data when you first look at the problem. But there's always a notion of consistency. You've got a notion of saying, if this one is like that and that one is like that, are they okay? Are they consistent with one another, yes or no? And then a bidirectional transformation is a thing that has two jobs. One is to say, check whether they're consistent, and the other is to say, if they're not consistent, then bring them into consistency by modifying either one or the other. Lenses is a special case where one end has strictly more data than the other. And in that case, you call it yank, don't you, not get, enclosure. Your yank is the thing that will bring the smaller amount of data into consistency, and your shove, or in the original conception, put, is the thing which will bring the two into consistency by modifying the larger collection of data. That's always the harder problem, because you might then have to, invent stuff that's not present in the smaller data.
Yeah, unsurprisingly, these names were taken.
Yeah. We always get this. So one of the things that the object-oriented BX community went kind of round and round about was the fact that, in general, a bidirectional transformation doesn't have to have that property, where one end of it will have all of the data. It might be that you've got two ends, and each of them has some data which is not contained in the other. And the classic example from the OMG standard is UML to RDBMS, which is the horrible problem reinvented, where you can say, well, okay, your UML model will have all kinds of information that's completely irrelevant to your RDBMS, and the RDBMS may have indexes and something that the UML knows nothing about. In the end, people have, there are all kinds of category theory papers and what have you that talk about how actually, you can always construct all of these for a certain class of things out of pairs of lenses, and you can do it in various different ways, and you can tie yourself up in knots like that. But then the question is, how do you actually want to program? So for a long time, there has been a wish to be able to program those general books, so to be able to write your programs under the assumption that you're going to be dealing directly with things, neither of which is an abstraction of the other. And we don't have good languages for doing that, really. And when you start thinking about the properties of those things, you quite quickly tie yourself in knots, because you find out that you can easily write down properties that you would like, and you can demonstrate that you can't have them. Things become a lot easier when you stick to lenses. And actually, pragmatically, that's probably the right thing to do. And back in sort of 2006, 2007, when people were thinking about it, one of the reasons for not thinking about it that way was the unreliability of the internet. Because the obvious way to solve this problem is to say, well, what you'll do is all the data you might ever be interested in should live in one place, and then everything else should be projections of that. And the point at which that went wrong was you said, well, you might not be able to connect to that place that's got all the data. And so then you might want to be able to do these sort of two-way connections between things which are symmetrically connected. And these days we sort of don't really believe in that problem anymore, because the internet is reliable enough that you can just say, well, you'll be online, or you'll be online soon enough. But
there's also the issue of administrative boundaries. So you may not want
yes.
to have everything in just one place, because
yes.
who knows which was the data.
Yes, absolutely. Yeah.
Thanks. Point me to a few papers. Or maybe I could just read this website. Is that enough?
Yeah, the website is a bit partial and not very up to date. So I think the last few years, I was part of a research project that was one of the contributors to it in the early days, but that's going back 10 years or so now, and more recently I don't think anybody's been very systematically updating it. So there'll be some good starting points there, but it's not up to date or comprehensive at all, and it's probably gives a rather partial view. One of the things that maybe is worth looking at, if you scroll down, there should be a link to, try the BX examples repository. And do consider contributing to that, because that's got quite a lot of interesting, or potentially interesting, examples from a number of different sources of bidirectional transformations that people have worked on and formalized in various different ways, or not formalized in various different cases. Yeah, so one of the motivations for this was to think about the different properties that you might or might not want bidirectional transformations to have. So correct and Hippocratic is Book's language speak for get put and put get between them. It comes to the same thing. undoability and history ignorance are among the properties that you often would like to have and don't, and correspond loosely to put. So that, yeah, there's some discussion down here. Mike Johnson is one of the people who's done a lot of work on that.
Thank you. It's become your talk now.
That's totally enough for me. Somebody else? Nobody else wants to say anything. Maybe we'll thank you again and move on to the next session.
So, yeah, well, this is not a talk. I'm going to say a few things anyway. And I have a couple of questions for you. So, let's see how it goes. Interesting. Oh, that works. Okay. So first of all, so earlier this week, Graham Hutton, who was the co-chair of FUNARCH last year, he said, "How was working with Perdita?" And I said, "It was a dream." And he said, "That's what I thought." So thank you, Perdita, first of all.
Michael didn't work.
No, that is not true. And I have numerous, specifically one piece of work. So there's the program committee, of course, that does the reviews. I want to point out that they didn't just do the reviews, but we always consider, for papers that are coming in, we always consider doing shepherding. And that happened in a number of cases. I think that's generally a good idea, especially for workshops where maybe you have some first-time authors. So thank you to the program committee. I think none of them is here in this room anyway. And I think only Richard is actually, well, Martin is somewhere around here. So if you see them, you might thank them. And Ilya's here, yeah. He's very busy now, though, preparing next year's ICFP. So, but if you were here last year, then you probably noticed, so the program is not quite as packed as it was then, and the room is also not quite as packed as it was then. So that raises some obvious, and this is only the second time around, so that raises a couple of questions, right? Is it worthwhile doing this again? Do we have the right format for doing this? I mean, this is something that Graham and I just made up last year, and we didn't know how well it was going to work or how suitable it was going to be. One thing a couple of people have said, well, I'll get to that, is it the right time in the sense of, is it the right day within the ICFP sort of days that we have? And maybe we can briefly talk, so if we answer the first question with yes, then we can talk about next year and onwards a little bit. So is this a worthwhile thing to do? So, well, you're here in this room, so maybe people not in this room would say no, but obviously I feel it's worthwhile, but I mean, you're kind of nodding, but why is it worthwhile? What do you think? I mean, I can say why I think it's worthwhile, but why do you think it's worthwhile?
Well, to me, this is the track that goes a bit more into the practical matters of applying functional programming, to do actual, not useful work, but actual real stuff.
Yeah.
I think it's worth talking about that.
Okay. Well, ICFP has definitely moved away from that. So, arguably, there's a little gap there. But I mean, of course, quite a few of the other workshops that are running right now also talk about some a little bit more specific practicalities. It's really an honest question. Why is it worthwhile to you? Right?
I think I agree with that, and there's also the experience reports. So there was one experience report ICFP, but then that's a big audience, right? So I mean, I think it's also nice to have an opportunity for the sort of more bigger scale or commercial things, but in a smaller environment than the full ICFP.
Yeah. Okay. Any other takes? So, I mean, I gave a talk last year on why I thought it was worthwhile, so I'm just going to repeat sort of my central point, which was that there's a huge communication gap between sort of the larger software architecture community and us, right? Not just a communication gap, there's just lots of stuff that they know that we don't, and the other way around. So you just pointed out that maybe the OMG would have benefited from importing more sort of semantics or functional programming. And I can, well, Marco talked about, you know, the object-oriented community has come out with all this stuff in domain-driven design, and some of that is useful to us, but maybe all of it, that is useful to us. And this workshop was definitely not designed to be the solution to that. It was supposed to be one building block, right? That in the grand puzzle that we're trying to fill would like play, you know, what would be one part. So if we think that, let me go, do we have the right format for this? I mean, we made a couple choices, right? In that, I mean, one definitely relevant choice was that there's a publication associated with the papers at the workshop, right? And we could have chosen not to do that, right? Either by not having like formal papers or not having the papers be a formal ACM publication, instead doing some kind of tech report, because we felt it was important to, if we're going to communicate, given there's, you know, X people here and maybe 4 people watching the live stream and maybe a couple people then watching the video afterwards, but that it's important to preserve the publication, right? So that other people beyond this room could look at it. But presumably, so that means though that the format is effectively like a small conference, right? Still, right? So it's, you know, somebody, you know, I used to run farm, and then, you know, one year somebody came in and said, we're putting the work back in workshop, right? And then actually had the audience involved in a little project, assembling a little hardware piece and doing a little programming on that, right? So in that sense, it's not a workshop, right? So is there, I mean, in principle, the call allows for other kinds of submissions, right? You could propose a panel of some sort or some, whatever, right? There's an open category even, but nobody's done that so far. Yeah.
Personally, I think the format, what the format provides is good, and I personally like having that kind of that range of options up to a full research paper. I think, you know, one way, you know, would be to lower the barrier of entry by offering. I mean, I'm not sure actually if this is offered. So, can you propose an extended abstract with, you know, can you write one page and send an extended abstract, or, you know, sometimes people have these with later deadline or lightning.
I'll have something to say about the deadline in a moment. Yeah.
So a lighter thing, because, you know, partly with a workshop, you know, you also want to have good talks, right? So,
Yeah.
I mean,
Yeah, unfortunately the deadline, as soon as you do a publication, has 2 bookends. And one of them is that it needs to be after the ICFP deadline, that it needs to be after ICFP notification, because in principle, I mean, nobody submits architecture or practical programming papers to ICFP anymore, apparently, but things were kind of predicated on that theory. But the idea is that people would be able to submit their rejected paper from ICFP, right? And on the other hand, the stuff at least that go into the publication, they go into a publication process, and you know what that was like, right? You communicate with the publication company, you know, you got to, whatever, get the right LaTeX incantations in place, and you got to go typically a few, I don't know if you've gone, but most people I've talked to have gone a few rounds with them. And the deadline that they originally proposed was 3 weeks earlier than the one that it was, and this really threw me back to the old days in ICFP when things were on paper, right? And so, strangely enough, I was workshop chair with Graham, right? And Graham had this Graham, who's always meticulously prepared, like had this process document that said, they will propose an unrealistic deadline for publication. You need to push back, and then it will be pushed back. And this was 15 years ago, so, so it felt exactly the same way around.
So I have an naive question. So you said that the submission date has to be no earlier than the ICFP rejection, and I get the reasoning, but you also said nobody submits this kind of
Yeah.
paper to ICFP.
So yeah, maybe that assumption is wrong.
Or could we just decide, we're not competing with ICFP for papers, we'll have our deadline earlier and have more time for
Yeah.
revisions and discussion?
I mean, so I have to say that we missed the original deadline, and we wrote an experience report. So I think we started writing after the first deadline in March. So I think, and also the ICFP, I think that's so entrenched in people's minds that the workshop deadlines are a bit later. I mean, it's catching the rejected papers but just as part of the bigger event.
Yeah. I mean, so one question is the thing is, right, a lot of the potential submissions or a lot of the actual submissions also are coming from industry, right? And so, of course, as an academic, right, specifically as an academic who's here, right, you have all this culture and education in writing papers, which you might not have when you are in industry, right? Are we providing the right, we do shepherding, which is something that happens basically after acceptance or conditional acceptance, right? A couple of authors are here. Did you feel that you got the right kind of support and the right amount of support? Okay. Yeah, well, you had, okay.
I think it also depends, it's also the company perspective, right? So whether people value, writing a paper, participation, and stuff. So it's, I think, in my experience, we all have an academic background, so this is totally normal. But yeah, it's interesting that there are all the sponsors tables outside, and some of them will have people from those companies who contributed in different ways. Some of them will have papers at conferences or experience reports, and the interaction that you need to utilise that connection.
But my thinking is it would be great to have more experience reports and papers, and that really is the core of an event like this. One thing I wonder is, so you said that we did shepherding, we did, but we didn't advertise that we were going to do shepherding.
Okay.
Are there people out
Really?
there who might write papers if they knew that shepherding was going to be available? Is there a community of people who don't submit papers because they're not very familiar with doing it and they think they don't know how to do it? Or
good point. Okay.
Ex-academics who do it, that's how they do it.
And this goes in a few other, your good point. Apparently we forgot to advertise, so.
I don't know whether it would make a difference or not.
No, I just checked, so we forgot. So this is an honest admission here.
This is going to be potentially very idiosyncratic. As I said, I'm an economist. What I'm looking for when I come here is very different, I guess, from the average person. But I think the few computer science conference or workshops that I've been to, what was most useful for me was, usually things like experience reports, but especially when it was quite applied in a way where I could tell, could I use that or not? That's kind of my main goal when I go to these things. So the closer to apply that is, the more helpful. I was just wondering whether something like a panel discussion where one sort of sets a problem that is probably quite common across a few things and has various people say how they have addressed it in a specific setting might be more interesting than, might have a higher density of what I've learned for the time spent as an audience member than seeing one person's approach to it. Like taking our continuations thing today, if that's really fitting you, then great. Otherwise you sit there and you're like, well, yeah, okay, but I would have preferred seeing 2 or 3 other approaches to stateful things on the web or something like that.
I'm very conscious of the fact that this is a very specific ecosystem, right? we're in, right? In terms of computer science conference, programming language conference, right? And things are definitely different in other communities, and I think we tend to forget. I think a lot of people here tend to take the current format that we have as given, right? And they forget really, they literally forget that there's a work-in workshop. And there's this natural, right, in computer science, things are kind of skewed in that the main publication venue is the conferences, so the conferences really are like journals. This means that everything else beneath it kind of moves up one step. But unfortunately, there's nothing below workshop, right, that would then take that place. So that sounds like a good idea.
There are different formats, right? So some places they have pre-proceedings or they only have abstracts like types, for example, and then they have something afterwards. So they're different.
Yeah. So the thing that we asked a bunch of people, Graham and I, when we started out, right? And it seemed that there were at least a few people for whom publication would be a substantial incentive, right, to send something in, right? So, for you?
I raise my hand because for me, in econ, it takes more like 3 or 4 years to publish something, but at the same time, they count all publications equally. So for me, this was a nice arbitrage opportunity.
Okay. Yeah. Well, very good. Very good.
It was genuinely the best.
Yeah. So, okay. That's good to know.
But sometimes in the future, I might be like, I don't need more papers right now. I actually rather have feedback.
Filled your quota for this year. Okay. Yeah. Okay. Yeah. So, ultimately, we can collect ideas here. This is now a very concrete question. I kind of only noticed yesterday that today is really crowded, right? As far as other workshops are concerned. If you're here, you might not have noticed, but for the racket talk, this room was full, and all these people are now in other workshops, right? Most of them anyway. So, and there's Haskell going on, there's the ML workshop going on, there's a new one called, I forget, something proper. There is the mini Canron workshop going on. There's Tidy going on, right? And definitely at sort of at some of these other venues, they definitely have overlapping interests, right? Whatever, all the Jane Street people are all about OCaml, so they tend to, OCaml is tomorrow, but a lot of them still hang out at the ML workshop today, I think. So if you can imagine for yourself right now when you're in this room, right, would things be different? There's a couple of alternatives. The obvious alternatives are the other workshop days, right? And so there was one before the conference, which was on Monday, right? And that one had, well, let's check the program, right? Maybe turn off dark mode. So this had farm, right? So workshop on art, they had the Erlang workshop. And a PLMW, and it had HOPE, higher order programming effects. So if FUNARCH had happened on that day, would you be here today? Honest question, right? Just
you would have less competition.
Yeah.
But then, some people have arrived just for the Haskell Symposium. They arrived today or last night, so you wouldn't get those extra people popping in and out. And it would also, if you also want, Haskell Symposium is obviously the biggest extra, I'm sure it must be the second biggest, right? So event. So then it makes it a very long week. So it's a very different. It's a bit like talking about parallel tracks or not. It's very different.
Yeah, well, the thing with the overlap is a two-edged sword because, the idea is then to get some people who are now at the Haskell Symposium into FUNARCH, right? But these people would still like to go to the Haskell Symposium, and so that means that they then have to suffer through 3 days of mechanized semantics before that happens.
It's difficult. Last year,
Yeah.
I did notice that you got, there were people who probably were, heavily involved in the Haskell Symposium who dropped into FUNARCH, and I noticed that the audience went up and down quite a lot during the day.
Yeah. So tomorrow would be, so what's going on tomorrow, that would be an alternative, right? So there's the Scheme workshop, there is the OCaml workshop, and there's the second day of the Haskell Symposium, right? Would that be better, we think? So let me float another idea that I'm never going to get past the ICFP steering committee, but to do it parallel to the last day of ICFP. I mean, we did get something like that past the steering committee or past the program committee. Is we have, my company runs a developer conference every year, Bob, and we did a special edition when ICFP was in Berlin in 2019, right? And I was able to convince Derek Dreyer to run it concurrent. I mean, Bob is not quite the same thing, but vaguely similar in sort of the kind of audience that might be interested. And I was able to convince Derek Dreyer to do it, I think, during the last day of ICFP. And I think that worked out really well. And in particular, maybe slightly to ICFP's disadvantage, because Bob was packed always, right? And so there was probably some people might have hung out at ICFP instead, or, so it's an idea to, so I mean, the worst they can do is turn me down, right? Should I ask them for that for next year, if we should do that?
Why did it work for Bob?
Huh?
Why do you think it worked for Bob?
I think it worked for Bob because, well, I'm going to vastly oversimplify, but Bob is a very practical conference, right? And we asked even the speakers that came over from ICFP to give sort of practically oriented talks. And ICFP has become just a much more theoretical conference in the last 10 years, I think, than it used to be. And so I think your interest is going, so the chance is higher that your interest is in one of these areas, but not in both, right? And that, right.
I mean, to me, that's a kind of different kind of thing. That's a bit like ICFP co-located with Splash. You get that synergy of two communities coming together, and it's kind of a one-off thing. I think it's a little bit different to have the interaction with the satellite workshop and the conference.
I mean, to me, it always seems strange that ICFP should be exempt from the conflicts that you have for the workshops, right?
Really?
Huh?
I thought that was normal.
Huh?
Yeah.
No, this has been, this.
ETAPS, for example, has these, so that has several conferences, and they're kind of during the week, and then the workshops are at the weekends. I thought it's pretty common, but I don't know. That's just not coming up with.
I mean, the basic question, right, is ICFP really, or is any given day of ICFP really of such general interest that all the 400 people here have to absolutely hear all the talks, right? So I might ask Ilya if there's a chance to do it on the last day of that. So that's, or somebody might ask because. So if we're going to do this again, there's a couple of issues, right? So each workshop obviously needs chairs, or at least one chair, and needs a program committee. It needs most importantly, it needs, well, let me correct that and just say submissions. Also, if we're going to perpetuate the workshop, then workshops generally have a little bit of governance to ensure that. And might be a little steering committee and and some charter or something like that written up. So it's been my great pleasure to be the chair last year and this year. There's this problem in that I'd not just like to have this workshop, I'd also like to submit this workshop to this workshop. And as a chair, I can't do that. So. that's insurmountable, I think. So I should note that if you're on the program committee, it's perfectly fine to submit, but if you're the chair, you can't, right? And so I would very much appreciate if somebody else chaired it. I mean, that would have, it would get my support, definitely. Obviously, there would have to be some support also to sort of carry over the institutional knowledge. So you don't have to say yes right here, but if you could conceivably see yourself chairing next year's workshop, I would appreciate a note, or if you know somebody that you might ask. This is also, the same kind of question goes for the program committee. I think we're going to do, or somebody's going to do, I always say we, but as sort of reflex, but I really shouldn't. There's going to be a slightly wider search for that, so I don't think that's a significant issue. My personal conclusion from this workshop is we didn't, so we got less submissions than we did last year. We also did less soliciting of papers than we did last year. And maybe those things go together, maybe they don't, I don't know. But my personal conclusion is that if we're going to continue doing this, or at least for next year, we should probably try much harder to talk to people personally. My feeling is, or not just my feeling, my impression is that there's a lot of people who have something in store, right? Who have experience writing larger scale functional programs, who are in a good position to frame some earlier work that they've done in architectural terms. I talk to a lot of people here who say, yeah, I got something, right? All I need to do, and we have concrete ideas of what they might do. All that needs to happen is that they need to be persuaded to write them up, right? So that would be, even if it's not the usual mode, we had a brief discussion of that for a workshop, but I think that's okay. I don't know if anybody sees a problem with that. And that, of course, that might impact what you might otherwise see as sort of an impartial and fair process, which I kind of don't subscribe to that view. But is there anything worth adding to that? I mean, I kind of said what my view is. So the third thing is then to establish some kind of governance. And so there's the third, so there's the chairs, there's the PC, well, a fourth thing, obviously, a fourth group of people. Well, as I said, the usual thing, and I think the thing that we're going to try and do now after this workshop is establish a little steering committee. The main job is to ensure that next year's workshop happens, even if they don't do the work, right? And have a few rules in place, and maybe carry over, a few notes on how that's done. Again, so this really should not be a whole lot of work, right? It's like 3 meetings a year or something like that. And maybe write a few emails to people. So if you can see yourself doing that, I would also appreciate that ping. So I'm going to refrain from doing that now, but I see Stefan nodding. So we'll see if I can convince him. Anything else we should discuss about what we're doing? Okay. Then that concludes our business. Let me put in a little bit of advertising, because probably it needs some advertising, because I don't know if you were here at the beginning of the week, you saw that there were tutorials, but they weren't scheduled yet. They have been scheduled now. So there's a tutorial tomorrow morning, which might also be interesting, because I'm also, we can certainly also discuss the industrial perspective of teaching functional programming. So it's not just if you are like a lecturer and have students, but also if you're interested in how to teach functional programming to your organization, then I will have a few things to say, or we can just have, we can kind of pool our knowledge on this. Lots of other people have experience with this, so but I certainly can say something on that. So if you're interested in that, I would love for you to be there. Come tomorrow at 9 o'clock, so I guess starting time changes again tomorrow morning. that concludes our business. Thank you for being here. Thank you, presenters. Thank you, Marco, for doing your talks, and hope to see you next year and even more people.